Stand for a moment in front of something impossible. Not impossible in the fantastical sense, but impossible in a way that is far more unsettling. Picture yourself at the base of a structure built thousands of years ago, stones fitted together with such precision that you cannot slide a piece of paper between them. No mortar, no modern tools. No cranes or lasers or computer-aided design. Just stone against stone, locked in an embrace so perfect that it has survived earthquakes, wars, and centuries of weathering. Modern engineers visit these places with their instruments, their measurements, their expertise, and they leave with more questions than answers. This isn't a story about what ancient people built. It is a story about what we lost, because here is the uncomfortable truth we don't often discuss. Human progress has never been a straight line pointing upward. It has been a jagged arc full of peaks and valleys, civilizations that rose to extraordinary heights and then collapsed, taking their knowledge with them. We like to imagine ourselves standing at the pinnacle of human achievement, looking back at primitive ancestors who knew less than we do. But what if that is not entirely true? What if scattered across our history are moments when people understood things we've forgotten? The evidence sits in plain sight. Structures that defy explanation, techniques we cannot replicate, materials whose composition remains mysterious even under electron microscopes. These aren't myths or legends. They're physical objects you can touch, measure, analyze, and yet the knowledge of how they were created has vanished as completely as if it never existed. The question that should keep us awake at night isn't whether ancient peoples were clever. It is what happened to everything they knew. Consider this. Technology isn't just objects. It is not the sword or the building or the tool itself. Technology is understanding. It is the accumulated knowledge of how to shape materials, how to solve problems, how to transform an idea in your mind into something real in the world. And understanding, it turns out, is fragile. It requires continuous transmission from one generation to the next. It needs teachers and students, masters and apprentices, written records and hands. On practice, break that chain at any point, and knowledge that took centuries to develop can disappear in a single generation. Throughout history, civilizations have reached remarkable heights. They've created wonders, and then something happened. War swept through, killing the craftspeople and burning the libraries. Natural disasters buried cities and scattered populations. Conquering armies deliberately destroyed the achievements of those they defeated, erasing not just buildings but the very memory of how those buildings were made. Sometimes the loss was intentional. Sometimes it was simply neglect, economic changes that made old techniques obsolete, practitioners who died before they could pass on what they knew. What is most troubling is that we may never know the full extent of what vanished. We can see the gaps where knowledge used to be. We find references in ancient texts to techniques that are no longer understood. We discover artifacts that shouldn't exist according to our timelines of technological development. We stand in front of engineering marvels that seem to require capabilities their builders weren't supposed to possess, and we're forced to confront an unsettling possibility. Our ancestors in some domains knew things we don't. This isn't about ancient aliens or lost civilizations from Atlantis. This is about human beings, people like us, who observed their world carefully, experimented tirelessly, and developed genuine expertise. They created techniques that worked, solutions that were effective, understanding that was real, and then, for reasons both tragic and mundane, that understanding was lost. The evidence remains, the knowledge does not. Across the world, in ruins and relics, in fragments and whispers, the remnants of lost technologies wait, not to prove we're inferior to our ancestors, but to remind us that knowledge is always more fragile than we imagine. Imagine watching your enemy's fleet approach across dark water, hundreds of ships, thousands of warriors, certain of victory, and then from the prows of your defending vessels, something impossible happens. Liquid fire erupts in roaring streams, arsing through the air like dragon's breath. It strikes the enemy ships and spreads instantly, clinging to wood and sail and flesh. Men dive into the sea to escape the flames, but the fire follows them down. It burns on the surface of the water itself, turning the ocean into an inferno. This is not imagination. This happened repeatedly for nearly 700 years. The weapon was called Greek fire, and it saved Constantinople from destruction more times than we can count. Historical accounts describe it with a mixture of awe and terror. Arab historians wrote of flames that could not be extinguished, that consumed entire fleets, that made the sea itself seem to boil. Byzantine sources speak of siphons mounted on ships, tubes that projected the burning liquid with tremendous force and accuracy. Enemy commanders learned to fear these weapons above all others. Some refused to engage Byzantine naval forces entirely, knowing that Greek fire could turn certain victory into catastrophic defeat within minutes. The psychological impact was as devastating as the physical destruction. How do you fight something that ignores every natural law you understand? The Byzantines understood what they possessed. They guarded the formula with paranoid intensity. Production was restricted to a single imperial facility. The recipe was never written down in full, never shared beyond a tiny circle of trusted individuals. Emperors passed the secret to their successors in whispered conversations. The few people who knew the complete formula took oaths of silence. Some sources suggest they faced execution if they revealed even fragments of the knowledge. This obsessive secrecy worked for centuries. No enemy ever captured the secret. No spy ever extracted the full formula. The Byzantines kept their advantage through careful control of information, and then they lost it anyway, not through espionage or conquest, but through something far more mundane. The empire declined, resources dwindled, the specialized facility where Greek fire was produced eventually closed. The last people who knew the complete formula died without adequate successors. By the time anyone realized what was happening, it was too late. The knowledge was gone, completely irreversibly. Modern historians can read accounts of what Greek fire did, but they cannot tell you definitively how it was made. Scientists have tried. For over a century, chemists have proposed theories. The mixture probably contained petroleum products, perhaps naphtha or refined crude oil from natural seeps. Quicklime might have been involved, creating intense heat when it contacted water. Sulfur and pine resin appear in some reconstructions. Certain combinations of these ingredients can produce flames that burn on water, but none of the modern recreations fully match the historical descriptions. None achieve the same sustained burning, the same resistance to extinguishing, the same terrifying effectiveness that made Greek fire legendary. We have approximations. We do not have the actual formula. What makes this loss particularly striking is what it reveals about Byzantine chemistry. They understood distillation processes. They knew how to refine petroleum products centuries before the Industrial Revolution. They had discovered combinations of materials that created specific, controllable reactions. This was sophisticated practical chemistry in an era we often characterize as ignorant of science. The Byzantines didn't have our theoretical framework, our periodic table, our understanding of molecular bonds. But they had something equally valuable: generations of careful experimentation, observation, and refinement. They knew what worked, and then that knowledge simply evaporated, leaving us with descriptions of effects we cannot quite reproduce and techniques we cannot fully explain. Greek fire shows us something crucial about how knowledge actually exists in the world. When we think about technology, we usually imagine objects: the sword, the machine, the building. But technology lives in 3 distinct layers, and losing any one of them can make the others useless. There is the artifact itself, the physical thing you can hold or see. There is the technique, the skill required to create it, the practiced movement of hands that know exactly how much pressure to apply and when. And deepest of all, there is the understanding, the conceptual framework that explains why something works the way it does. We often possess 1 or 2 of these layers while missing the 3rd entirely. Walk into any museum and you'll find artifacts we cannot replicate. We can measure them, analyze their composition, admire their craftsmanship, but the technique that created them is gone. The hands that knew how to coax metal into particular shapes, how to blend materials in precise proportions, how to achieve results that seem impossible with the tools available at the time, those hands turned to dust centuries ago. The understanding they possessed, the accumulated wisdom of what works and what doesn't, died with them. We're left holding evidence of capabilities we cannot fully explain. The fragility becomes obvious when you examine how technological knowledge actually survives. It requires continuous practice. You cannot preserve a skill simply by writing it down. Try learning surgery from a textbook without ever touching a patient, or mastering pottery without ever centering clay on a wheel. Certain knowledge lives only in repeated doing, in the feedback between action and result, in the subtle adjustments that no written description can fully capture. Break the chain of practice and the skill vanishes within a generation. It requires infrastructure, specialized tools, specific materials, supply networks that deliver exactly what is needed when it is needed, economic systems that support the practitioners while they refine their craft over years of apprenticeship. Remove any piece of this supporting structure, and the technology collapses even if the knowledge technically still exists. It requires cultural support. Societies must value the skill enough to invest resources in it, to grant status to its practitioners, to create institutions that preserve and transmit it across generations. When cultural priorities shift, when new values replace old ones, entire domains of expertise can become obsolete almost overnight. We don't have to look to ancient history to see this pattern. In the 1970s, the United States sent human beings to the moon. The Saturn V rocket that lifted them there remains the most powerful machine ever built. Then the program ended. The specialized manufacturing facilities closed. The companies that produced unique components went out of business or shifted to other products. The engineers who understood the intricate details of how everything fit together retired. By the early 2000s, when new plans for lunar missions emerged, NASA faced an uncomfortable reality. Much of the knowledge of how to build a Saturn V had been lost. Not the blueprints, those still existed, but the tacit knowledge, the manufacturing expertise, the suppliers who knew how to create specific parts to exact specifications. Gone. If this can happen to space-age technology within a few decades, imagine what occurred across centuries and millennia. The pattern repeats throughout history. Civilizations rise, develop sophisticated capabilities, then collapse or transform. The knowledge scatters. Future generations find remnants and struggle to understand what their ancestors achieved. Sometimes the loss is accidental, the natural consequence of disruption and change. But sometimes it is deliberate. Conquering armies destroy the libraries and workshops of defeated peoples. Religious authorities suppress knowledge they consider dangerous or heretical. Economic changes make old techniques unviable, and practitioners take their expertise to the grave. What we're exploring in this documentary isn't just a catalogue of lost technologies. We're examining the nature of knowledge itself, how it survives and how it dies. We're asking whether the capabilities we've lost are truly beyond recovery, or whether they're simply waiting, hidden in plain sight for us to remember how to see them. There is a fortress in the mountains above Cusco, Peru, that shouldn't exist. Not in the sense that it is impossible, but in the sense that we cannot fully explain how it came to be. Sacsayhuaman sits on a hillside, its walls composed of stones so massive that standing beside them makes you feel like an insect. Some of these blocks weigh more than 200 tons, but their size isn't the mystery. What defies explanation is how they fit together. Run your hand along the joints between these stones and you'll feel something unsettling. There are no gaps. None. The surfaces meet with such precision that you cannot insert a knife blade between them, cannot even slide a piece of paper into the seam. Modern laser measurement confirms what your fingers tell you. These surfaces match with tolerances measured in fractions of millimeters. And this isn't the fit between two simple rectangular blocks. These are polygonal shapes, each one unique, with multiple faces and angles. Imagine trying to cut two irregular stones, each weighing hundreds of tons, so that 12 different contact points between them all align perfectly. Now imagine doing this without computers, without laser measuring tools, without diamond-tipped cutting equipment. The conventional explanation involves copper tools, abrasive sand, and extraordinary patience. Ancient masons supposedly pounded and ground these surfaces over months or years, constantly checking the fit, making minute adjustments until perfection was achieved. This explanation isn't ridiculous. Copper tools and sand abrasives can cut stone. Patient craftspeople can achieve remarkable precision. But when you stand in front of these walls, when you really look at what was accomplished, a question emerges that is difficult to ignore. Where is the evidence that this method was actually used at this scale? Experimental archaeologists have demonstrated stone cutting with copper tools. They've achieved impressive results with blocks weighing hundreds of pounds. But the largest stones at Sacsayhuaman weigh 400,000 pounds. That is not a difference of degree. It is a difference of kind. The engineering challenges of working with masses that large, of moving them, positioning them, checking their fit, making adjustments, multiply exponentially with size. Yet no one has successfully demonstrated the proposed techniques on stones approaching this scale. What makes the mystery deeper is what we haven't found. No massive stockpiles of worn-out copper tools where they should be if thousands were used and discarded. No clear evidence of the grinding and pounding that should have scarred the surrounding area. No intermediate attempts, no practice stones, no partially completed blocks showing the progression of technique. The finished product exists in stunning perfection, but the trail of how it was created seems almost deliberately absent. Walk through Sacsayhuaman and you'll notice something else peculiar. Many stones show smooth, almost glassy surfaces in places, as if the rock had been heated or treated with something that altered its texture. Other blocks have what appear to be scoop marks, curves and depressions that look almost molded rather than cut. These features don't match what you'd expect from pounding and grinding with hard tools and abrasive sand. They suggest different processes, techniques we might not have considered because they don't fit our assumptions about what ancient peoples could or should have known. Similar precision appears at other sites separated by thousands of miles and supposedly built by cultures with no contact. Pumapunku in Bolivia features blocks with perfectly flat surfaces and precise right angles that meet aerospace manufacturing tolerances. The Osirian in Egypt contains massive granite blocks fitted with the same uncanny precision. Across continents and centuries, ancient builders achieved results that modern stonemasons, even with power tools, struggle to match economically. We can do it, but it requires expensive equipment, skilled operators, and significant time. How did ancient workers, allegedly armed only with copper chisels and stone hammers, achieve the same results faster and more consistently? The question isn't whether ancient peoples were intelligent or capable. They clearly were. The question is whether we've correctly understood their methods. Perhaps they knew something about working stone that we've forgotten. Techniques involving heat application, chemical treatments, or mechanical methods that leave no archaeological trace because the tools were simple or organic, or perhaps they possessed knowledge we haven't rediscovered because we've never imagined it was possible. The stones remain precisely fitted, silently holding secrets that our theories haven't quite managed to unlock. In the Bekaa Valley of Lebanon, there is a stone that modern engineers look at and quietly shake their heads. It is called the Stone of the Pregnant Woman, and it weighs roughly 1,000 tons. That is 2 million pounds of solid limestone cut from bedrock with clean edges and smooth surfaces. Nearby, incorporated into the foundation of the ancient temple complex at Baalbek, sit 3 even more impossible stones. The trilithon. Each block weighs approximately 800 tons, and they rest 20 feet above ground level, fitted so precisely that the seams between them are nearly invisible. These aren't theoretical weights. They've been measured, calculated, verified, and they present a problem that gets larger the more you think about it. The biggest mobile crane currently in operation can lift about 3,000 tons under ideal conditions, with extensive preparation, perfect ground stability, and carefully distributed load. Most heavy lift cranes max out well below 1,000 tons. These are massive machines, technological marvels that require teams of engineers to operate. They need stable foundations, often specially prepared ground, and they move incredibly slowly under maximum load. The logistics of transporting a 1,000-ton stone today would involve months of planning, specialized equipment, and costs running into millions of dollars. Yet at Baalbek, stones of this magnitude were not only moved from the quarry but lifted into precise position in a complex structure, and this happened roughly 2,000 years ago. The conventional explanation suggests massive labor forces, perhaps thousands of workers using ropes, levers, and wooden rollers. Ramps might have been built to raise the stones gradually. Lubrication with water or oil could have reduced friction. These methods are plausible in theory. Ancient peoples understood basic mechanical principles. Lever and pulley systems can multiply human effort dramatically. But when you start calculating the practical requirements, the numbers become staggering. How many ropes would you need to safely distribute a 1 million-pound load? How thick would they have to be? How many people could physically fit in a space where they could pull effectively? Easter Island presents a different version of the same mystery. The moai, those iconic stone heads with bodies, were carved from volcanic rock in a single quarry and then transported across the island to various coastal locations. The largest moai successfully moved weighs about 80 tons. Experimental archaeologists have demonstrated that teams using ropes and wooden sledges can move replica moai, tilting and pivoting them across relatively flat ground. These experiments are impressive and instructive, but the largest statues remain at the quarry unfinished or abandoned. Some weigh over 200 tons. The experiments that succeeded with smaller versions haven't scaled up to match the largest achievements. The island had limited timber. The terrain between quarry and coast includes slopes, rough ground, and areas where the proposed techniques would face serious challenges. Egypt multiplies the mystery across hundreds of miles. Granite obelisks weighing hundreds of tons were quarried at Aswan in the south and transported to Luxor, Cairo, and other sites in the north. The Nile provided a water route which helps explain long-distance transport. Barges could carry immense loads that would be impossible to move overland. But getting the stones from quarry to barge, and from barge to final position, still required engineering solutions we don't fully understand. The unfinished obelisk still lying in the Aswan quarry weighs over 1,000 tons. It was being carved as a single piece of stone before a crack halted the project. If it had been completed, how would it have been extracted from the bedrock, moved to the river, loaded onto a barge without capsizing, transported hundreds of miles, offloaded, and then erected vertically? Each step presents challenges that push the limits of what we think was possible with available technology. Some researchers have proposed more sophisticated techniques, counterweight systems that reduce the effective mass being moved, pivot point methods that allowed massive stones to be tilted and rotated rather than lifted directly, sound or vibration technologies that ancient texts occasionally reference but that we don't fully understand. The problem with these alternative theories is the same problem facing conventional explanations: lack of clear archaeological evidence. We don't find the massive ramps, the complex pulley systems, the specialized equipment that any of these approaches would seemingly require. What we find are the stones themselves, moved and positioned with undeniable success, but with frustratingly few clues about method. What seems certain is that ancient builders possessed engineering knowledge that went beyond what could be figured out through trial and error in a single generation. This was sophisticated, systematic understanding passed down through master-apprentice relationships, refined over centuries of practice. When those civilizations fell, when the building traditions were disrupted or deliberately destroyed, that knowledge scattered like ashes in wind. The Great Pyramid of Giza contains a secret that went unnoticed for thousands of years. It is not hidden in some secret chamber or encoded message. It is built into the structure itself, visible to anyone who measures carefully enough. Take the perimeter of the pyramid at its base and divide it by twice the height. The result approximates pi to a degree of precision that seems difficult to explain as coincidence. The ancient Egyptians supposedly didn't have a formal concept of pi, yet there it is, encoded in millions of tons of limestone, accurate to several decimal places. Look closer and more patterns emerge. The pyramid's alignment to true north is accurate to within a tiny fraction of a single degree, a precision that wasn't matched by European builders until the invention of sophisticated surveying instruments. The dimensions relate to the proportions of the Earth itself. The ratio of the pyramid's height to its base perimeter is the same as the ratio of the Earth's radius to its circumference. Coincidence piled upon coincidence starts to look like something else. It starts to look like knowledge. Across the Mediterranean, Stonehenge marks the summer solstice sunrise with unnerving accuracy. Stand in the center of the stone circle on the longest day of the year, and the sun rises directly over the healed stone. This alignment has been understood for centuries. What is less widely known is that the structure appears to function as an astronomical calculator, tracking not just solar events but lunar cycles as well. The positions of the stones, the relationships between different elements of the complex encode information about eclipse cycles, seasonal variations, celestial mechanics. Someone designed this. Someone understood exactly what they were building and why. But perhaps the most shocking evidence of ancient astronomical sophistication was pulled from the Mediterranean Sea in 1901. The Antikythera mechanism lay in a shipwreck for 2,000 years before sponge divers recovered it, corroded and mysterious. For decades it sat in museum storage, too degraded to understand. Then X-ray analysis revealed what was inside. Gears, dozens of precisely cut bronze gears arranged in a mechanism of stunning complexity. When researchers reconstructed how it worked, they discovered an astronomical computer capable of tracking the positions of the sun, moon, and planets, predicting eclipses and calculating celestial events years in advance. This device was built around 100 BCE. Nothing remotely comparable appears in the historical record until medieval Islamic astronomers created similar instruments over 1,000 years later. The precision of the gears, the sophistication of the mathematical understanding required to design it, the astronomical knowledge embedded in its calculations, all of it suggests a level of technical and scientific capability that shouldn't have existed. Not because ancient Greeks were incapable, but because we thought this kind of sophisticated instrument making belonged to a much later era. The Antikythera mechanism destroyed that assumption. It proved that ancient peoples could achieve things we didn't think they could achieve, which raises an uncomfortable question. What else could they do that we don't know about? The mathematics required for these achievements wasn't simple arithmetic. Tracking planetary motion requires understanding cycles within cycles, predicting where celestial bodies will be months or years in advance. Encoding pi in a pyramid's dimensions requires precise measurement and complex calculation. Creating gear ratios for an astronomical computer demands mathematical sophistication that we typically associate with much later periods. These weren't primitive peoples making lucky guesses. These were systematic thinkers who observed, calculated, and built with deliberate precision. And then that knowledge vanished. The Library of Alexandria burned, taking with it hundreds of thousands of texts, including works on mathematics, astronomy, and engineering we know about only through references in surviving sources. Spanish conquistadors destroyed almost every Mayan codex they encountered, erasing astronomical tables and mathematical knowledge that had taken centuries to compile. Indigenous traditions worldwide were disrupted or deliberately destroyed, and with them went oral knowledge of celestial cycles, seasonal patterns, and natural phenomena observed and recorded over generations. What is particularly tragic is that we've lost not just the information but the conceptual frameworks. Ancient astronomers didn't separate their observations from spiritual or philosophical understanding. Their mathematics was intertwined with cosmology. Their architecture embodied their knowledge of the heavens. When we look at these alignments and relationships now, we're missing the full context that made them meaningful. We can measure the precision, we can verify the mathematical relationships, but we're seeing fragments of systems that once formed coherent wholes, integrated ways of understanding that our modern categorical divisions don't quite capture. The stones and mechanisms remain. The complete knowledge they represented does not. We've inherited the artifacts of sophisticated intellectual traditions we can admire but cannot fully reconstruct. Hold a Damascus blade up to the light and you'll see water flowing across steel. Not actual water, but patterns that ripple and swirl like currents in a stream. Dark bands against lighter metal, organic and alive in a way that modern steel never looks. These weren't decorative etchings added after the fact. The patterns emerged naturally from the forging process itself, visible evidence of the blade's internal structure, and that structure was extraordinary in ways the smiths who created it could never have imagined. When modern scientists examined Damascus steel under electron microscopes, they found something that shouldn't exist. Carbon nanotubes, structures at the molecular level that materials scientists didn't deliberately create until the late 20th century. These nanotubes gave the steel properties that made it legendary: flexibility that prevented shattering when the blade struck armor or bone, hardness that allowed an edge fine enough to split falling silk, durability that kept that edge through battle after battle. Warriors across the medieval world recognized Damascus blades as superior to anything else available. They paid fortunes for them, and they were right to. The metallurgical properties were genuinely exceptional. The blades came from smiths working primarily in the Middle East, though the steel itself originated elsewhere. The process apparently required wootz steel, a particular type of crucible steel imported from India. This wasn't ordinary iron. The ore contained trace elements, vanadium, chromium, manganese, in proportions that turned out to be crucial. The smiths didn't know about trace elements or carbon nanotubes. They knew that steel from certain sources worked in certain ways, produced superior blades. Generations of masters passed their knowledge to apprentices through years of hands-on training. The temperature of the forge had to be exact. The rhythm of hammering mattered. The timing of heating and cooling couldn't vary. None of this was written down in detail because you couldn't really write it down. How do you describe in words the color of steel at the precise moment it is ready to fold? How do you capture in text the feel of metal under the hammer when the temperature is exactly right? For centuries, this system worked perfectly. Master smiths trained successors. The knowledge flowed from generation to generation like the patterns on the blades themselves. Damascus steel production reached its peak between the 16th and 18th centuries, and then it ended. By the early 1800s, no one could make it anymore. The technique was simply gone. The reasons for the loss are still debated. The most likely explanation involves multiple failures happening simultaneously. The Indian mines that produced Wootz steel with exactly the right composition apparently became depleted or closed. Trade routes that had supplied materials for centuries were disrupted by political changes and warfare. The economic landscape shifted as firearms replaced swords as primary weapons. Suddenly there was less money in bladesmithing, less incentive for young people to endure years of apprenticeship to master a difficult craft. Master smiths aged and died without training adequate successors. When the last man who knew the complete process died, the knowledge died with him. Modern metallurgists have tried to bring it back. Using electron microscopy and chemical analysis, they've determined the composition of original Damascus steel. They've experimented with forging techniques, trying to recreate the conditions that produced those distinctive patterns and superior properties. Some attempts have come impressively close. Bladesmiths today can create steel with watering patterns that look similar. They can achieve hardness and flexibility approaching what the originals possessed. But there is still debate about whether modern recreations are genuinely identical to historical Damascus steel or merely similar results achieved through different methods. We've reverse engineered an approximation. Whether we've recovered the actual lost technique remains uncertain. What makes this loss particularly instructive is what it teaches about how technical knowledge survives or fails to survive. Damascus steel required an ecosystem, specific raw materials from specific sources, economic conditions that supported specialized craftsmen, a cultural transmission system that moved tacit knowledge from master to apprentice through years of immersive practice. Remove any element and the whole structure collapses. The smiths didn't lose the knowledge because they were careless or ignorant. They lost it because the complex system that sustained their craft broke down. The materials disappeared. The economics changed. The teaching chain was severed, and once broken, that chain proved extraordinarily difficult to repair. You cannot recover tacit knowledge from written descriptions alone. You need living masters to teach living students. When that line breaks, what took generations to develop can vanish within a lifetime. In the heart of Rome stands a building that shouldn't still be standing. The Pantheon was completed in the year 126. Nearly 2,000 years later, its dome remains the largest unreinforced concrete dome ever built. Not the largest ancient dome, the largest dome, period. Modern engineers can build taller structures, wider spans, more dramatic shapes. But they do it with steel reinforcement, with materials and techniques the Romans never had. The Pantheon's dome is just concrete and brick, holding its own weight through nothing but the way it was designed and the material it was made from. And it is still there, still functional, still waterproof, weathering the centuries with a patience that makes our modern construction look temporary by comparison. But the Pantheon isn't even the most impressive demonstration of Roman concrete's properties. For that, you have to look underwater. Roman harbour installations, piers and breakwaters built 2 millennia ago and submerged in seawater ever since remain intact. More than intact, scientific analysis has revealed something remarkable. The concrete has actually gotten stronger over time. Seawater, which destroys modern concrete through chemical reactions that create cracks and deterioration, has done the opposite to Roman structures. The material has reacted with the marine environment in ways that enhance rather than degrade its strength. Modern concrete doesn't do this. Build a marine structure today with conventional concrete, and you're looking at a lifespan measured in decades, maybe a century with careful maintenance and protective measures. The chemistry of seawater attacks the bonds in modern concrete relentlessly. Reinforcing steel corrodes, cracks develop, structures weaken. Roman concrete somehow turns this process backwards. Research published in recent years identified the mechanism. A rare mineral called aluminum tobermorite forms within the concrete over time, growing in cracks and gaps, essentially healing the material as it ages. Modern concrete doesn't create this mineral. Roman concrete does. The difference comes down to formulation and ingredients. Romans used volcanic ash, specifically ash from deposits around Pozzuoli near Naples, mixed with lime and seawater in proportions that created unique chemical properties. The volcanic ash contained minerals that reacted with seawater in beneficial ways, triggering the formation of those strengthening crystals. Modern concrete uses Portland cement, a material developed in the 19th century that is optimized for fast setting and high early strength. It is extremely useful for modern construction, allowing rapid building at enormous scale, but it doesn't have the long-term durability characteristics of the Roman formulation. The knowledge of how to make Roman concrete was lost when the empire collapsed. The supply networks that brought volcanic ash from Pozzuoli to construction sites across the empire broke down. The engineering expertise dispersed as centralized Roman administration fragmented. Medieval builders constructed magnificent cathedrals and castles, but they used different materials and different techniques. The specific formulation that made Roman concrete exceptional simply wasn't passed down. For more than 1,000 years, the secret sat hidden in plain sight, embedded in structures everyone could see, but nobody quite understood. It wasn't until modern materials science developed sophisticated analytical tools that researchers began unraveling what made Roman concrete special. Even now, we're still discovering new aspects of its chemistry. Each study reveals additional layers of sophistication in a material we once dismissed as primitive. The irony is sharp. We can build faster, bigger, with materials that set in hours rather than months. But we cannot build concrete structures we're confident will last 2,000 years. The Romans could and did. This matters beyond historical curiosity. Modern concrete production is responsible for roughly 8% of global carbon emissions. The industry is desperately seeking more sustainable alternatives. Roman concrete, which uses less lime than modern formulations and whose ingredients require less energy to process, represents a potentially valuable model. For marine construction, where durability in seawater is critical and modern concrete performs poorly, understanding Roman techniques could revolutionize how we build ports, offshore platforms, and coastal defenses. Lost technology isn't just about the past. Sometimes it is about solutions to present problems. Answers we stopped using before we fully understood the questions. There was a color so valuable that wearing it could get you executed. Tyrian purple, the deep shade that marked emperors and kings, came from the sea, specifically from the murex snail, a creature that produces a tiny amount of pigment in a specialized gland. Extracting enough dye to color a single garment required thousands of snails, weeks of careful work, and knowledge that was guarded more carefully than gold. Phoenician dye workers controlled the process, passing secrets from master to apprentice in workshops along the Mediterranean coast. The technique involved harvesting the snails, extracting the glands, fermenting them under specific conditions, and processing the resulting liquid until it transformed into that legendary purple. Different fermentation times, different exposures to light and air produced different shades from deep violet to crimson. When the Phoenician dye industry collapsed, that knowledge collapsed with it. Modern chemists can synthesize the chemical compound responsible for the color, but the traditional process, with all its subtle variations and accumulated expertise, is gone. Egyptian blue tells a different story. This wasn't extracted from nature. It was synthesized, one of humanity's first artificial pigments, created by heating silica, lime, copper compounds, and alkali to temperatures between 800 and 1000 degrees Celsius. The process required precise temperature control, specific ratios of ingredients, and timing that couldn't vary. Get any element wrong, and you'd produce useless slag instead of brilliant blue pigment. Ancient Egyptians mastered this process roughly 5,000 years ago. The pigment appears on tombs, temples, and artifacts across the Mediterranean world for millennia. Then, sometime after the Roman period, production stopped. The knowledge of how to make it vanished completely. For over 1,000 years, no one knew what Egyptian blue was chemically or how it had been created. Modern analysis finally unlocked the formula, but also revealed something the ancient makers never knew. Egyptian blue fluoresces in infrared light. Illuminate it with infrared and it glows, emitting light at wavelengths invisible to human eyes but detectable with modern sensors. This property has potential applications in medical imaging, telecommunications, and security systems. The ancient Egyptians created a material with properties they couldn't perceive, properties we're only now learning to exploit. They did this through empirical observation and experimentation, refining the process across generations until it worked reliably, never understanding the quantum mechanical reasons why. Look at ancient Peruvian textiles in museum collections, and you'll see reds so vibrant they appear freshly dyed. These fabrics are centuries old, some over 1,000 years, yet the colours haven't faded the way modern dyes fade when exposed to light and air. The pigments came from cochineal insects processed through techniques that stabilize the colour in ways modern textile chemists still don't entirely understand. Maya blue presents an even stranger mystery. This pigment, which adorned temples and murals across Mesoamerica, combines organic indigo dye with inorganic clay minerals in a molecular structure that creates extraordinary resistance to acids, alkalis, heat, and biodegradation. The exact process of creating this hybrid material was lost with Maya civilization. Modern researchers have proposed methods, but debate continues about whether current recreations truly match the original or merely approximate it. Medieval European glassmakers produced colours that modern manufacturers struggle to match. Cathedral windows glow with reds so deep and pure that contemporary glassmakers, despite advanced chemistry and precise temperature control, cannot consistently replicate them. The secret apparently involved adding gold or copper in specific forms under specific conditions. Guild secrecy meant these techniques were never widely shared. When economic changes disrupted the guild system, the knowledge dispersed and faded. What unites these lost colours is sophisticated chemistry achieved without theoretical understanding. Ancient dyers and pigment makers didn't know about molecular structures, oxidation states, or pH levels. They knew what worked. They knew that certain materials combined in certain ways under certain conditions produced reliable results. This knowledge came from countless experiments, generations of trial and error, careful observation of what succeeded and what failed. When economic conditions changed, when cheaper synthetic alternatives appeared, when guild systems collapsed or civilizations fell, all that accumulated wisdom could vanish within decades. We're left with examples of what was achieved 1,000-year-old colours that still glow, pigments with properties we're only now discovering, but without the complete knowledge of how they were created. There is a plant on ancient coins from Cyrene, a Greek city, state in what is now Libya. The image appears repeatedly, a distinctive stalk with clustered flowers, sometimes shown alongside the city's patron deity. This wasn't decorative symbolism, this was economics. The plant represented on those coins was silphium, and it was valuable enough to serve as currency itself, important enough to store in the imperial treasury alongside gold and silver. Ancient writers describe it as something close to miraculous, a contraceptive that actually worked, a digestive aid that relieved everything from indigestion to more serious ailments, a flavouring so prized that wealthy Romans paid extravagant prices for even small amounts. And it grew in only one place on Earth, a narrow strip of North African coast, refusing all attempts at cultivation elsewhere. For centuries, silphium was harvested and exported across the Mediterranean world. Demand never seemed to diminish. The plant became so integral to the economy of Cyrene that the city's prosperity rose and fell with the silphium trade. Roman texts mention it repeatedly, describing its uses, lamenting its increasing rarity, recording its climbing price. Then, sometime around the 1st century, references to silphium stop. The last documented stalk was reportedly given to the Emperor Nero. After that, nothing. The plant was gone, harvested into extinction before anyone thought to preserve it, before anyone understood that a resource once abundant could simply vanish forever. The mystery deepens because we cannot identify what silphium actually was. Ancient descriptions mention a tall stalk, yellow flowers, a thick root, and a distinctive smell. Some accounts compare it to giant fennel. Others suggest relationships to plants in the carrot family. Modern botanists have proposed various candidates. Asafoetida, still used as a spice in some cuisines, shares certain properties and might be a relative, but whether it is the same plant, a related species, or something entirely different remains speculation. We have ancient coins showing its image, texts praising its virtues, and absolutely no certainty about its botanical identity. When the last silphium plant died, it took with it not just its genes, but all the accumulated knowledge of how to use it effectively. That knowledge represented generations of discovery. Someone had to first identify the plant as useful rather than poisonous. Someone had to experiment with preparation methods, dosages, applications for different ailments. This didn't happen overnight. It was accumulated wisdom, refined through countless trials, passed down through oral tradition and practical demonstration. When silphium went extinct, all that understanding became irrelevant. You cannot apply botanical knowledge to a plant that no longer exists. This pattern repeats across human history. Indigenous peoples worldwide developed extensive pharmacopoeias, detailed knowledge of local plants and their medicinal properties. These weren't superstitions or folk tales. They were empirical systems built on observation and experimentation. A plant that relieves fever when prepared one way causes vomiting when prepared another, and does nothing when prepared a third way requires systematic testing to understand. Traditional healers knew which plants treated which conditions, how to prepare them, what dosages to use, what combinations worked synergistically. Much of this knowledge was never written down. It lived in practice, passed from healer to apprentice through hands-on teaching. When colonization disrupted or destroyed these cultures, when traditional practices were suppressed, when languages died, and elders passed away without successors, vast libraries of botanical knowledge vanished. Modern medicine occasionally rediscovers what was lost. The rosy periwinkle, a plant from Madagascar, produces compounds now essential for treating certain cancers. Traditional healers knew the plant had medicinal properties long before pharmaceutical companies isolated the active chemicals. Artemisinin, derived from sweet wormwood and now a frontline treatment for malaria, comes directly from traditional Chinese medicine. Chinese healers used this plant for fevers for centuries before modern science understood why it worked. These successes are encouraging, but also sobering. They prove that traditional botanical knowledge contained genuine medical value. They also highlight how much might have been lost, how many other plants possessed useful properties that no one documented before the knowledge disappeared, how many effective treatments were dismissed as primitive superstition and forgotten before anyone tested them scientifically. Modern ethnobotanists work with desperate urgency, trying to document traditional plant knowledge before the last generation that possesses it dies, but they're fighting time and cultural disruption. Every year, languages go extinct, taking botanical terminology with them. Traditional healers die without trained successors. Forests are cleared, eliminating species before they're studied. Silphium stands as a warning. Once the plant is gone, once the knowledge holders are gone, recovery becomes impossible. We're left with references and regrets. Ancient coins, showing something we can no longer identify. Pick up a human skull from a burial site in Peru, dated to around 400 BCE, and you might notice something that stops you cold. A neat circular hole in the cranium, edges smooth and deliberately shaped. This wasn't trauma from battle or accident. This was surgery. Someone drilled into this person's skull while they were alive, removed a section of bone, and then the patient survived long enough for the bone to begin healing. We know this because we can see the regrowth, the body's attempt to close the wound, evidence that the person lived days or weeks or even months after the procedure. This is trepanation, and it was performed successfully thousands of years ago across multiple continents by people who had never heard of bacteria, who didn't understand intracranial pressure, who possessed no modern anesthesia. The precision is what is most striking. These weren't desperate hackings by desperate people. The holes are clean, deliberately shaped, often showing multiple procedures on the same individual at different times. Someone knew what they were doing. Someone understood enough about human anatomy to know you could cut into the skull without immediately killing the patient. Someone had developed techniques for managing pain, preventing infection, and caring for the wound during recovery. We don't know exactly how they did any of this. What we know is that it worked often enough that the practice continued for centuries. Ancient Indian medical texts describe procedures that sound like they belong in a modern surgical manual. The Sushruta Samhita, compiled around the 6th century BCE but likely containing much older knowledge, details surgical techniques with startling specificity. Cataract surgery performed by inserting a curved needle to displace the clouded lens. Rhinoplasty, reconstruction of noses damaged in battle or punishment, using forehead flaps rotated down to create new nasal structures. Removal of bladder stones through perineal incisions, cesarean sections. These weren't theoretical possibilities. The text provides step-by-step instructions, describes over 120 specialized instruments, and discusses post-operative care. This was practical knowledge refined through practice, taught through apprenticeship. The sophistication extended to understanding principles we think of as modern. Ancient Egyptian medical papyri, particularly the Edwin Smith papyrus, dated to around 1600 BCE but likely copied from much earlier sources, demonstrate systematic approaches to trauma care. The text describes 48 cases organized by body region from head to spine, each with examination procedures, diagnosis, and treatment recommendations. The language is clinical, rational, free of the magical incantations that appear in other Egyptian medical texts. For certain injuries, the text states plainly that nothing can be done, an acknowledgement of limits that reflects honest observation rather than mystical thinking. What enabled these capabilities? Knowledge of anatomy, certainly. Egyptian embalmers working with the dead provided opportunities to understand internal structures. Indian physicians may have gained anatomical knowledge through similar means or through observation of battle injuries and accidents. But knowledge alone isn't enough. You need instruments designed for specific tasks. The Sushruta Samhita describes scalpels, scissors, forceps, needles, saws, each crafted for particular procedures. You need infection control. Egyptian physicians used honey, which we now know has antimicrobial properties, and various resins that served similar purposes. You need pain management. Ancient surgeons had access to alcohol, opium, cannabis, and other plant-based substances that could dull sensation enough to make procedures bearable. Then, much of this knowledge disappeared from Europe. When classical civilization collapsed, the teaching hospitals closed, the libraries burned, the unbroken lines of master training apprentice were severed. Much of what survived did so only in Arabic translations preserved by Islamic scholars who maintained medical traditions while Europe entered darker centuries. Some procedures were lost entirely. Rhinoplasty, performed routinely in ancient India, didn't reach Europe until the 16th century when a physician encountered the technique and brought it back, presenting it as a novel discovery. Centuries of European patients had lived with facial disfigurement, while the knowledge of how to repair it existed elsewhere, inaccessible due to cultural and linguistic barriers. Medieval European prohibitions against dissection, based on religious beliefs about the sanctity of the body, prevented physicians from gaining the anatomical knowledge their ancient predecessors possessed. Surgical knowledge atrophied. When surgery was performed, it was often by barbers rather than physicians, considered crude mechanical work rather than learned medicine. Only gradually, across centuries, did European medicine relearn what had been known and practiced in ancient Egypt, India, and Greece. The knowledge hadn't been impossible. It had simply been lost, waiting to be rediscovered by people who thought they were innovating when they were actually remembering. Ancient Chinese physicians compiled lists of thousands of medicinal plants, each with specific therapeutic applications documented in texts that span millennia. These weren't random collections of folklore. They were systematic pharmacopoeias describing which plants treated which conditions, how to prepare them, what dosages to use. Modern research, equipped with tools to analyze chemical composition and test efficacy, has found something remarkable. Many of these traditional uses work exactly as described. Arsenic compounds, carefully processed to reduce toxicity, prove effective against certain leukemias. Qinghao, sweet wormwood, contains artemisinin, now a frontline anti-malarial drug that has saved millions of lives. Ephedra, used for respiratory conditions for over 2,000 years, contains ephedrine, a bronchodilator still used in modern medicine. The ancient physicians didn't know about molecular structures or receptor binding. They knew what worked. Ayurvedic medicine in India employed mercury and sulfur compounds, substances we now recognize as potentially toxic. Yet analysis of traditional preparations reveals sophisticated processing techniques that transform these materials into forms with reduced toxicity and apparent therapeutic value. The mercury isn't administered as pure metal or simple salts. It is subjected to repeated heating, grinding with plant materials, and combining with other substances in sequences that alter its chemical form. Modern analytical chemistry can identify what these processes produce. What remains mysterious is how ancient practitioners developed these techniques without understanding the underlying chemistry. They could see molecules, they could measure oxidation states. They worked through observation and experimentation, refining methods across generations until they achieved reliable results. The pharmaceutical knowledge went beyond identifying useful plants. Ancient healers developed sophisticated extraction and preparation methods. They knew that some compounds required alcohol to extract effectively. Others needed water, still others required oils. They understood that heat could concentrate certain properties while destroying others. They created tinctures, decoctions, powders, and pills, each preparation method suited to specific therapeutic goals. The Ebers Papyrus, an Egyptian medical text from around 1550 BCE, describes over 700 remedies using hundreds of different ingredients from plants, minerals, and animal sources. Modern analysis has identified many of these ingredients as containing compounds appropriate for their described uses. Willow bark for pain, containing salicylic acid, the precursor to aspirin. Honey for wounds with antimicrobial properties. Garlic for infections, containing compounds we now know have antibacterial effects. How did they figure this out? There were no controlled clinical trials, no double-blind studies, no peer-reviewed journals. The process was empirical observation extended across generations. Healers tried different treatments, noted what worked and what didn't, shared knowledge with colleagues and students, refined techniques based on accumulated experience. Successful treatments were retained and improved. Unsuccessful ones were abandoned. Over centuries, this process built extensive pharmacological knowledge. It wasn't perfect. Ancient medical texts contain remedies that modern science shows are ineffective or even harmful, but they also contain genuine therapeutic knowledge, insights that took modern pharmacology decades to rediscover. Much of this knowledge was lost or deliberately suppressed. During the scientific revolution, traditional medicine was often dismissed as superstition, its practices banned or marginalized in favor of approaches considered more rational. Colonial powers suppressed indigenous healing traditions, disrupting the transmission of knowledge that had been maintained for centuries. Only later did researchers discover that many traditional remedies contained legitimate therapeutic compounds. The loss was just the specific remedies. It was the context, the accumulated understanding of when to use which treatment in what combinations for which specific presentations of disease. We might have recovered a recipe from an ancient text, but without the surrounding knowledge, the diagnostic framework that guided its use, the variations for different patients, the supporting treatments that enhanced its effectiveness, the recipe alone is incomplete. Today, pharmaceutical companies engage in bioprospecting, systematically searching traditional medicine for new drug candidates. They collect plants used by indigenous healers, screen them for active compounds, develop profitable drugs from what they find. This raises uncomfortable questions about ownership and compensation. The knowledge being monetized was developed over generations by cultures that shared it freely as part of their healing traditions. When that knowledge was dismissed and disrupted, those cultures lost not just medical capabilities but entire systems of understanding health and healing. What is becoming clear is that ancient medical systems represented valid approaches to healthcare, different from but not inferior to modern medicine. They were based on careful observation, systematic experimentation, and accumulated experience. In dismissing them wholesale as primitive or superstitious, we likely lost insights that could enhance modern practice. Complementary approaches to healing that addressed aspects of health our current systems overlook. When Spanish conquistadors first saw Tenochtitlan, the Aztec capital, they thought they were hallucinating. The city rose from the middle of a lake connected to shore by causeways, surrounded by what appeared to be gardens floating on the water itself. Rectangular plots of brilliant green stretched across the lake's surface, separated by canals where canoes glided between rows of crops. The Spanish estimated the city's population at over 200,000 people, all fed by agriculture that seemed to defy the limitations of available land. They weren't looking at magic. They were looking at chinampas, an agricultural system so productive and sophisticated that we still haven't fully replicated it. Chinampas weren't actually floating, though they appeared that way from a distance. They were artificial islands built in the shallow parts of the lake system, constructed through a process that required remarkable ecological understanding. Farmers would stake out rectangular plots in the water, typically about 30 meters long and 2 to 3 meters wide. They'd build up the plots with layers of mud dredged from the lake bottom, alternating with vegetation and organic matter. Willow trees planted around the perimeter sent roots down through the structure, stabilizing it and preventing erosion. The result was a raised agricultural platform surrounded by water. On all sides, the soil constantly enriched by nutrient-rich lake sediment. The productivity was extraordinary. Chinampas could support 7 harvests per year through continuous cultivation, yields that make modern industrial agriculture look inefficient by comparison. The surrounding water provided constant irrigation, eliminating drought risk. It moderated temperature, protecting crops from both heat and occasional cold snaps. The canals attracted birds that fed on insects, providing natural pest control. Transportation was effortless. Farmers simply loaded canoes with harvested produce and paddled directly to market. The system integrated aquaculture seamlessly. Fish and waterfowl lived in the canals between chinampas, their waste enriching the water that fed the crops, creating a closed-loop ecosystem where nothing was wasted. The knowledge required to build and maintain this system went far beyond simple farming. You needed to understand soil composition and how to create growing medium that would support continuous cropping without depletion. You needed to manage water flow to prevent stagnation while ensuring proper irrigation. You needed to know crop rotation patterns that maintained productivity year after year. You needed structural engineering skills to build islands that wouldn't collapse or erode despite constant exposure to water. You needed ecological understanding to create a system where multiple elements, crops, fish, birds, water plants, interacted beneficially rather than competing destructively. When the Spanish conquered Tenochtitlan in 1521, they inherited a city whose food system they didn't understand and ultimately couldn't maintain. Over subsequent centuries, they drained much of the lake system, partly to prevent flooding, but also to create European-style farmland that made sense to colonial administrators. The chinampas were gradually destroyed. The knowledge of how to construct and manage them was disrupted as Aztec culture was systematically dismantled. Some chinampas survived in Xochimilco, now a district of Mexico City, and they still produce crops today, but the scale and sophistication of the original system are lost. At its peak, chinampas covered perhaps 12,000 hectares and fed the majority of a massive urban population. What survives now is a fraction, maintained more for tourism and cultural preservation than as a serious agricultural system. The loss becomes more poignant when you consider modern agricultural challenges. We face soil depletion from continuous cropping, water scarcity in many agricultural regions, the environmental damage from chemical fertilizers and pesticides, the carbon footprint of transporting food long distances from farm to consumer. Chinampas addressed all these issues. The system was sustainable indefinitely, enriching rather than depleting soil. It required no irrigation infrastructure beyond the natural lake system. It used no chemical inputs, relying on natural nutrient cycles and pest control. It allowed food production immediately adjacent to urban consumers. Modern attempts to revive chinampa techniques encounter a frustrating problem. We have historical descriptions. We can see surviving examples. But the accumulated expertise, the subtle knowledge of how to manage the system optimally, the generations of experience encoded in practice rather than text, that knowledge died with the culture that created it. We're left trying to engineer an approach to agriculture that could address some of our most pressing current challenges, working from fragments of understanding that once formed a complete and elegant whole. Walk through the Peruvian highlands and you'll encounter staircases built for giants. Agricultural terraces climb mountainsides at impossible angles. Thousands of platforms stacked one above another, some reaching altitudes where modern agronomists insist cultivation shouldn't be possible. These structures weren't simple earthworks. Cut into any terrace wall and you'll find sophisticated layering, foundations of carefully fitted stones providing structural stability, layers of gravel ensuring drainage, smaller stones and clay creating water retention, and finally topsoil enriched with organic matter. The engineering isn't obvious until you understand what these terraces accomplished. They modified microclimates, the stone walls absorbing heat during the day and releasing it at night, extending growing seasons in areas where frost could strike any month of the year. Many of these terraces, built 500 or 1,000 years ago, remain structurally sound and, when cultivated using traditional methods, prove more productive than flat fields at comparable altitudes. Yet the complete knowledge of how to construct and optimally manage them has eroded. We can see what was built. We can measure the dimensions and analyze the construction, but the accumulated understanding of exactly how to orient terraces for specific crops, how to manage water flow to prevent both drought and waterlogging, which crops to plant where based on subtle variations in microclimate, that knowledge existed as practice and observation, passed from farmer to farmer across generations. When those lines of transmission were disrupted by conquest, colonization, and rural depopulation, much of the expertise dispersed like morning fog. Beneath the deserts of Iran, invisible from the surface, run ancient water highways called qanats. These underground channels tap aquifers in mountain foothills and transport water through tunnels to arid lowlands, sometimes across distances of 30 or 40 miles. The engineering precision required is extraordinary. The gradient must be exact, too steep, and the water flows too fast, eroding the channel too shallow, and sediment accumulates, blocking flow. Ancient Persian engineers somehow surveyed these routes and maintained proper gradient across miles of underground construction. They dug vertical shafts every 50 meters or so for excavation, ventilation, and maintenance, creating surface features that look like chains of craters marching across the landscape. Building a qanat required specialized knowledge of hydrology, geology, and surveying. It was dangerous, skilled work passed through master-apprentice relationships. Some qanats still function after 1,000 years, but the expertise to design and construct new ones has largely vanished. The knowledge holders are gone, and with them went the accumulated wisdom of how to read landscapes for water, how to calculate gradients without modern instruments, how to maintain these systems across generations. In the Philippines, rice terraces carved into mountainsides 2,000 years ago still produce crops, recognized as such marvels of agricultural engineering that they're designated World Heritage Sites. Yet elders in the communities that maintain them will tell you that crucial knowledge is fading. The original construction involved not just physical engineering, but spiritual and social dimensions, rituals that governed planting and harvest, communal labor systems that maintained the structures, traditional ecological knowledge about pest management and soil fertility. Modernization has disrupted these integrated systems. Young people leave for cities. Chemical fertilizers replace traditional composting methods. The terraces remain, but the complete knowledge system that created and sustained them is fragmenting. In the deserts of Arizona, archaeologists have mapped canal systems built by the Hohokam people that once spanned hundreds of miles, diverting water from rivers to irrigate fields in areas that now seem too arid for agriculture without modern infrastructure. These weren't simple ditches. They were engineered networks with precise gradients, distribution systems, and maintenance protocols that kept water flowing to thousands of acres of cropland. The Hohokam civilization collapsed around 1450, and the knowledge of how to design and maintain such extensive irrigation networks disappeared with it. Later settlers found the canal traces but could replicate the system: sophistication. What united these various systems was something beyond engineering skill. It was deep, integrated understanding of local environments. The builders knew hydrology, soil science, climatology, and ecology not as separate academic disciplines, but as unified knowledge applied to solving practical problems. When these societies collapsed or were disrupted, That environmental knowledge, refined across generations of observation and experimentation, scattered and faded, leaving us with impressive physical remnants but incomplete understanding of the wisdom that created them. In the span of a single century, we've lost more than 75% of agricultural crop diversity. That is not a projection or estimate. It is a documented disappearance of plant varieties that took millennia to develop, erased in 3 generations by the spread of industrial agriculture and its preference for standardized, high-yield crops. But the loss goes deeper than genetics. With those vanished varieties went the accumulated knowledge of how to cultivate them, when to plant them, how to save their seeds, how to process their harvests. We've lost not just plants but entire systems of agricultural understanding. Walk through traditional farming communities in the Andes and elderly farmers can still name potato varieties their grandparents grew, varieties that no longer exist. There were thousands once, each adapted through generations of selection to specific conditions. One variety thrived at high altitude where frost came early. Another tolerated the drier soils of certain slopes. A third resisted particular diseases common in wetter microclimates. This wasn't redundancy, it was agricultural insurance. Biodiversity that meant crop failure in one variety didn't mean starvation because others would still produce. Those varieties are largely gone now, replaced by a handful of commercial cultivars bred for yield and transportability rather than adaptation to local conditions. Mesoamerican maize tells the same story. Indigenous farmers cultivated hundreds of distinct varieties, each with specific properties. Some matured quickly for short growing seasons. Others produced kernels that ground into flour with particular textures for specific traditional foods. Some grew tall to provide shade for companion crops. Modern hybrid corn, descended from a tiny fraction of this original diversity, dominates now. The traditional varieties survive mostly in seed banks, frozen in liquid nitrogen, genetic material preserved but disconnected from the knowledge of how to actually grow and use them. Ancient grain varieties like emmer, einkorn, and spelt once fed civilizations. They fell out of cultivation as modern wheat varieties proved easier to harvest and process with industrial equipment. The knowledge of how to grow these ancient grains, how to thresh them efficiently with traditional methods, how to grind and bake with their different gluten structures, that knowledge faded as the last farmers who worked with them aged and died. We're now trying to revive these crops for their nutritional properties and climate resilience, but we're essentially starting from scratch, relearning what was once common knowledge. What disappeared with these crop varieties was more than just genetic material. Traditional agriculture involved sophisticated understanding of ecological relationships. Farmers knew which crops grew better when planted together, how companion planting could deter pests or improve yields through complex interactions we're only now beginning to understand scientifically. They knew that rotating certain crops in certain sequences maintained soil fertility, that planting at particular times based on weather patterns or lunar cycles aligned with plant biology in ways that optimized germination and growth. Much of this was dismissed as superstition by agricultural modernizers. Yet modern research keeps validating traditional practices. Those companion plantings actually do repel pests through chemical signals or attract beneficial insects. Those traditional rotations actually do manage soil nutrients effectively. The timing that seemed based on folklore often aligns with biological rhythms we now measure with scientific instruments. The consequences of this loss become clearer as industrial agriculture faces new challenges. Modern crops, bred for genetic uniformity, show vulnerability to diseases and climate stress. An entire region's harvest can fail because every plant shares the same genetic weakness. Traditional varieties developed through centuries of selection in diverse conditions often contain resistance traits we desperately need, but many of those varieties are extinct. The genes are gone. The knowledge of which variety worked where and why is gone with them. Seed banks preserve what they can, storing genetic material against future need. But frozen seeds aren't living knowledge. They can't tell you which variety your grandmother planted on the north-facing slope, how she saved seeds from the strongest plants when she knew the moment was right for harvest. That knowledge lived in practice, in the relationship between farmer and land and plant, refined across generations through attention and adaptation. When the last farmer who knows dies, when the last seed of a variety fails to germinate, that particular thread of human agricultural knowledge breaks permanently. The Library of Alexandria burned, though exactly when and how remains disputed. What isn't disputed is what was lost. Not just scrolls and papyrus, but centuries of accumulated human understanding. The library had been the intellectual center of the ancient world, drawing scholars from across the Mediterranean and beyond, housing perhaps 400,000 texts. Greek plays that we know existed only because other authors mentioned them. Historical accounts of civilizations whose stories are now permanently silenced. Scientific treatises describing observations and theories we can only glimpse through fragments quoted in works that did survive. Mathematical texts that might have accelerated human understanding by centuries if they'd been preserved. Medical knowledge that could have saved lives. Astronomical observations recorded over generations, all of it reduced to ash through a combination of warfare, neglect, and deliberate destruction. We possess perhaps 7 complete plays by Sophocles. Ancient sources tell us he wrote over 120. The rest are gone, lost when the library and other repositories burned. Aeschylus wrote perhaps 90 plays, we have 7. Euripides wrote perhaps 92, we have 19. The greatest works of Greek theatre, texts that shaped Western culture for centuries, survived as a tiny fraction of what once existed. Everything else burned. We'll never read those plays, never know what insights they contained, never experience what ancient audiences experienced when they were performed. The gaps in our knowledge are permanent. The destruction happened gradually, then catastrophically. Fire during Julius Caesar's campaign in 48 BCE damaged part of the collection. Budget cuts and political instability led to neglect. Eventually, changing religious attitudes toward pagan learning made the library's contents seem not just irrelevant but dangerous. The final destruction, whenever it occurred, erased what remained. When knowledge is centralized in a single location, its vulnerability becomes total. One fire, one deliberate act of destruction, and centuries of scholarship vanish permanently. Baghdad's House of Wisdom met a more sudden end. In 1258, Mongol forces under Hulagu Khan sacked the city. The House of Wisdom, where scholars had spent centuries preserving and expanding upon Greek, Persian, and Indian knowledge, was systematically destroyed. Astronomical observations, medical texts, mathematical treatises, philosophical works, all thrown into the Tigris River. Contemporary accounts claimed the river ran black with ink for days, the dissolved text of thousands of manuscripts staining the water as they disintegrated. Knowledge that had survived the fall of previous empires that had been carefully translated and studied and built upon was destroyed in weeks of deliberate vandalism. Spanish conquistadors and missionaries brought a different kind of catastrophe to Mesoamerica. They encountered Mayan writing and sophisticated script encoding knowledge of astronomy, mathematics, history, and culture. Unable or unwilling to understand it, they burned nearly everything they found. Diego de Landa, a Franciscan bishop, organized the burning of Mayan books in 1562, destroying what he considered works of the devil. Only 4 codices survived the systematic campaign of cultural destruction. 4 books preserved from an entire civilization's written knowledge. The Maya had also carved extensive texts in stone on temples and monuments. Those inscriptions survive, but we can barely read them. We lost the Rosetta Stone equivalent when the codices burned. We can glimpse that the Maya understood astronomical cycles with remarkable precision, that they had sophisticated mathematics including the concept of zero. But the full extent of their knowledge is locked in inscriptions we cannot fully decipher because the texts that would have taught us their meaning were deliberately destroyed. In India, the Nalanda University Library was said to have burned for months when invaders set it aflame. The exact date is uncertain, sometime around 1200. The library housed countless Buddhist texts, philosophical treatises, works on medicine, logic, grammar, astronomy. Monks had copied and studied these texts for centuries, preserving knowledge from across Asia. The fire reduced it all to ash. Some knowledge survived in texts that had been copied and distributed to other monasteries. Much did not. What makes these losses particularly tragic is their permanence. The scrolls in Alexandria often existed as single copies or limited editions. When they burned, they were gone forever. We know some of what was lost because other authors referenced those works, quoted passages mentioned their existence. These fragments tantalize us with glimpses of sophisticated knowledge that existed but cannot be recovered. We stand in the present looking back at gaps in human understanding, knowing that people once had answers to questions we're still asking, but the books that contained those answers turned to ash centuries ago, leaving silence where knowledge once lived. Every 2 weeks, somewhere in the world, a language dies. The last person who spoke it as their first language, who thought in its grammar and dreamed in its vocabulary, passes away. And with them goes more than words. An entire way of understanding the world vanishes. The language contained knowledge about local ecosystems encoded in precise terminology that other languages lack. It held navigation techniques preserved in chants, agricultural wisdom embedded in seasonal stories, medicinal plant knowledge passed through generations in oral traditions. All of it disappears, not because it was written down and the books were burned, but because it was never written down at all. It lived only in human memory and practice, and when the last speakers die, the knowledge dies with them. The Tasmanian Aboriginal peoples possessed sophisticated understanding of their island's ecology, accumulated over thousands of years of continuous habitation. They knew which plants were edible, and how to manage fire to maintain productive landscapes, how to read weather patterns specific to their region. Disease and violence brought by European colonization decimated the population. Survivors were displaced, their children forbidden to speak their languages or practice traditional ways. Within a few generations, almost all of that knowledge was gone. We have fragments preserved by early ethnographers who bothered to record what they could. But the full depth of Tasmanian Aboriginal understanding, the nuanced knowledge of place and practice, is lost. The last native speaker of a Tasmanian Aboriginal language died in the 19th century, and with her went understanding we can never fully recover. Before European contact, the Americas held linguistic diversity that staggered early observers. Hundreds of languages, each representing a distinct way of organizing knowledge about the world. Many of these languages encoded sophisticated understanding of astronomy, agriculture, and ecology. They weren't primitive or simple. They were complex systems refined over millennia, capable of expressing concepts that European languages struggled to capture. Conquest, disease, and deliberate policies of forced assimilation destroyed most of them. Children were removed from families and sent to schools where speaking their native language resulted in punishment. Traditional practices were banned. Economic changes made old ways of life impossible to maintain. Languages that had persisted for thousands of years disappeared within a century. The knowledge contained in these oral traditions was different from written knowledge, but not inferior to it. Polynesian navigators could cross thousands of miles of open ocean, finding tiny islands using techniques encoded in chants and stories. They read wave patterns, star positions, bird behavior, cloud formations, an integrated system of environmental observation that allowed them to navigate with precision that astounded European sailors with their compasses and charts. This knowledge was transmitted orally, taught through direct experience and traditional instruction methods. Much of it has been lost as traditional navigation gave way to modern technology. The elders who knew are dying. Efforts to preserve the knowledge face the challenge that you cannot fully capture it in writing. Navigation knowledge requires feeling the ocean swell beneath the boat, reading subtle signs that text cannot adequately convey. Ethnobotanists work with desperate urgency, trying to document indigenous plant knowledge before the last generation that possesses it dies. An elderly healer in the Amazon knows which plants treat which conditions, how to prepare them, what dosages to use. This knowledge took centuries to develop through careful observation and experimentation. But the healer's children may have moved to cities, may be more interested in modern medicine than traditional practices. When the healer dies, the knowledge goes with them unless someone has documented it. But documentation is incomplete at best. The written record captures recipes but might miss context. Which symptoms indicate this plant rather than that one? What time of year to harvest for maximum potency? How to identify the right species among similar-looking plants? Recording a language isn't the same as keeping it alive. A language is a living system, evolving through use, carrying knowledge that is activated through practice and context. Knowledge embedded in endangered languages is often place-specific, tied to particular ecosystems and cultural practices. Remove the language from its context, from active use, and much of its meaning becomes inaccessible. We're living through a mass extinction of languages and the knowledge systems they carry. Each loss diminishes human cultural diversity and eliminates understanding of the world that took millennia to develop. This isn't ancient history, it is happening now, today, as you listen to this. And once it is gone forever. For centuries, craft guilds controlled specialized knowledge like state secrets. A young person who wanted to learn glassmaking, metalwork, or fine textile production would apprentice for years, sometimes a decade or more, learning not just techniques but the accumulated wisdom of generations. The system worked because it was economically sustainable. Master craftspeople earned enough to justify the time invested in training successors. Guilds maintained quality standards and controlled markets, ensuring their members could make a living. The knowledge flowed from master to apprentice in an unbroken chain stretching back centuries. Then economic conditions changed, and the chain shattered. Venetian glassmakers on the island of Murano developed formulas and techniques so valuable that the Venetian Republic treated them as strategic assets. Glassmakers were forbidden to leave Venice. Those who tried faced severe punishment, even death. The Republic understood that knowledge was wealth, that these techniques gave Venice a monopoly on certain luxury goods that generated enormous profit. For generations, this system preserved secrets effectively. But when the glass industry eventually declined in Venice, when competition emerged elsewhere, when tastes and markets shifted, some of those closely guarded techniques disappeared. The last masters who knew certain formulas died without adequate successors, and knowledge guarded for centuries vanished within a generation. Damascus steel followed a similar trajectory. We discussed the metallurgical sophistication earlier. What is worth emphasizing here is how it was lost, not through catastrophe but through economics. When firearms replaced swords as primary weapons, the market for exceptional blades collapsed. The elaborate, expensive process of creating Damascus steel became economically unviable. Master bladesmiths couldn't justify years of apprenticeship for a craft with shrinking demand. The knowledge required continuous practice to maintain. When young people stopped learning because the economic incentives disappeared, the accumulated expertise of centuries evaporated within decades. Industrialization accelerated this pattern across countless crafts. Factories could produce more goods faster and cheaper than artisans working by hand. From an economic perspective, this was progress. From a knowledge perspective, it was catastrophic loss. Traditional craftspeople possessed nuanced understanding of materials that factory production didn't require. A master woodworker knew how different woods behaved, how grain patterns affected strength, how to work with imperfections rather than around them. A textile artist understood fibers at an intuitive level that came from years of hands-on experience. This wasn't just skill, it was tacit knowledge, understanding that cannot be fully conveyed through writing or even demonstration. It lives only in practice, in the feedback between hand and material, in problem-solving creativity that comes from deep familiarity. When the economic foundation supporting these crafts collapsed, the knowledge began dying. Traditional boat-building techniques that produced vessels perfectly adapted to local waters, built without metal fasteners using sophisticated joinery. Japanese timber frame construction methods that created earthquake-resistant buildings without nails, using only precisely cut joints. European lace, making so intricate that a single piece might require months of work. All of these face extinction not because they're inferior, but because they're economically uncompetitive with modern alternatives. The irony emerges when we rediscover that traditional methods sometimes produced superior results. Traditional boat designs that handle certain sea conditions better than modern hulls. Timber frame buildings that have survived earthquakes that destroyed concrete structures. Handmade textiles with durability and properties that mass production cannot match. By the time we recognize the value, the knowledge is often gone. We're left reverse, engineering from surviving examples, trying to understand what master craftspeople knew intuitively. Efforts to preserve traditional crafts face fundamental challenges. Master craftsperson programs, cultural heritage initiatives, artisan revivals, all attempt to maintain knowledge that is becoming economically obsolete. But without viable economic models, preservation becomes artificial. Young people cannot afford to spend years learning techniques that won't support them financially. Museums and cultural programs can document and display, but they cannot fully preserve living knowledge that requires continuous practice to maintain. The broader pattern is uncomfortable to acknowledge. Market forces optimize for efficiency and profit, not for knowledge preservation. Capitalism is extraordinarily good at producing goods cheaply and at scale. It is terrible at valuing cultural knowledge, craftsmanship, or techniques that don't generate competitive returns. Valuable expertise is routinely discarded because it is not profitable to maintain, regardless of cultural significance or technical merit. This happens quietly, without villains or dramatic events. Markets shift, cheaper alternatives appear. Young people choose different careers, and within a generation, knowledge that took centuries to develop simply doesn't exist anymore. Researchers at MIT recently did something that would have pleased ancient Roman engineers. They recreated Roman concrete using formulas derived from chemical analysis of 2,000-year-old samples and guidance from historical texts. They mixed volcanic ash, lime, and seawater in proportions the Romans might have used, then waited. What they observed confirmed what analysis had suggested. The concrete did indeed form aluminum tobermorite crystals over time, creating a self-healing mechanism that modern concrete lacks. In specific applications, particularly marine environments, the recreated Roman formulation outperformed contemporary concrete. This wasn't just historical curiosity. It was recovered knowledge with practical applications, a lost technology brought back through careful experimentation. But the process also revealed something crucial. Recreating ancient techniques requires more than following recipes. The researchers had to understand ratios, yes, but also curing times, application methods, the sequence of mixing, the way materials interact under different conditions. Ancient texts rarely capture this level of detail because the people writing them assumed certain knowledge was obvious, shared understanding among practitioners. Recovering lost techniques means rediscovering not just what was done, but how, through trial and error, through experimentation that reveals the tacit knowledge texts cannot convey. Experimental archaeologists attempting to understand how ancient Egyptians cut stone have demonstrated that copper tools used with sand as an abrasive can indeed cut granite. The experiments work. Copper saws and drills, when combined with quartz sand, will slowly abrade through even hard stone, but the process is extraordinarily time-consuming and physically exhausting. Cutting through a granite block the size of those found in pyramids would require weeks or months of continuous work. This raises uncomfortable questions. Was this actually the primary method? Or did ancient masons possess supplementary techniques we don't understand? The experimental success proves possibility but doesn't eliminate mystery. Perhaps there were methods for softening stone, for applying heat in ways that made cutting easier, for using tools or techniques that left no archaeological trace. The experiments show us what could have been done. They don't necessarily show us what was done. Easter Island Moai transport experiments offer similar insights and limitations. Teams using ropes, wooden sledges, and human labor have successfully moved replica moai across relatively flat ground. The experiments demonstrate that the proposed methods are viable for smaller statues over limited distances, but the largest moai weigh over 200 tons and were moved across rough terrain. Scaling the experimental successes up to match the largest achievements remains problematic. The experiments prove that basic principles work. They don't fully explain how those principles were applied at the extreme scales ancient islanders somehow managed. Traditional iron smelting experiments reveal how much tacit knowledge matters in ancient technologies. Researchers following historical descriptions can produce workable iron from ore using techniques ancient smiths would recognize. But they've also discovered that slight variations in temperature, timing, or material preparation produce dramatically different results. The ore needs heating to a specific range. Too cool, and it won't reduce properly. Too hot, and the iron absorbs too much carbon, becoming brittle. The fuel needs proper airflow. The proportions need accuracy. The timing of various steps requires judgment that comes from experience. Ancient smiths knew these things intuitively, through years of practice, through feedback from countless attempts. Modern researchers are rediscovering this knowledge through systematic experimentation. documenting what the ancients knew but never wrote down because it was embodied knowledge understood through doing. What experimental archaeology teaches is respect. Ancient peoples weren't guessing or stumbling toward solutions. They were systematic, observant, capable of sophisticated problem solving. The experiments also reveal the limitations of written knowledge. You cannot fully capture in text the feel of clay at the right moisture content, the sound of bronze at proper pouring temperature, the visual cues that indicate the correct moment for critical steps. This knowledge lived in practice, passed through demonstration and supervised experience. When that transmission line broke, the written descriptions that survived proved insufficient for complete recovery. The experiments have limitations. Demonstrating that something is possible doesn't prove it was actually done that way. We might achieve similar results through entirely different means. Thor Heyerdahl's expeditions proved that ancient peoples could have crossed oceans in reed boats, but proving possibility doesn't prove it actually happened. Still, experimental archaeology shifts our understanding. It reveals that solutions we assumed were impossible were often quite achievable with different approaches. It shows that ancient peoples faced complex problems and developed effective solutions. Each successful recreation recovers a fragment of lost knowledge, brings us closer to understanding how our ancestors achieved what they did. But each success also reveals how much context we lack, how much of the full knowledge system remains beyond our grasp. The Antikythera mechanism sat in a museum for decades, a corroded lump of bronze pulled from an ancient shipwreck, its significance completely unrecognized. Archaeologists knew it was old, knew it was mechanical, but could they determine what it did or how it worked? The corrosion obscured too much detail. Then X-ray analysis and CT scanning revealed what was hidden inside. Gears within gears, differential mechanisms of stunning sophistication, tiny inscriptions explaining astronomical calculations. The device was an astronomical computer from around 100 BCE, capable of tracking solar and lunar cycles, predicting eclipses, calculating planetary positions. Without modern imaging technology, this would have remained a mysterious artifact, its true nature forever hidden beneath corrosion. With it, we recovered knowledge of ancient technological capability that rewrote our understanding of what Hellenistic Greeks could achieve. Electron microscopy revealed secrets in Damascus steel that the smiths who forged it never knew existed. When researchers examined the blade structure at microscopic scales, they found carbon nanotubes, structures at the molecular level that materials scientists didn't deliberately create until the late 20th century. These nanotubes explained the steel's legendary properties, the combination of hardness and flexibility, the ability to hold an edge through repeated use. The ancient smiths were manipulating materials at scales they could perceive, controlling processes they didn't theoretically understand, achieving results through empirical refinement that we now recognize as sophisticated materials engineering. The discovery explained why recreating Damascus steel proved so difficult. We weren't just trying to match a recipe. We were trying to reproduce nanoscale structures created through processes the original makers could describe because they could see what they were creating. Spectrographic analysis transformed our understanding of ancient materials. Point the instrument at ancient glass, pigment, or metal, and it reveals precise chemical composition. Egyptian blue contained copper, calcium, and silicon in specific ratios heated to exact temperatures. Medieval glass incorporated elements we didn't expect. Ancient bronzes showed alloy compositions that varied systematically by purpose. Different formulas for tools versus ornaments versus weapons, indicating sophisticated understanding of how composition affects properties. None of this was written down explicitly. The knowledge lived in practice. Modern analysis recovers the formulas, but not the full understanding of why those specific compositions were chosen or how craftspeople achieved such consistent results. DNA analysis of ancient seeds opens windows into lost agriculture. Researchers can identify crop varieties from archaeological sites, mapping how domestication proceeded, discovering varieties that no longer exist in cultivation. Some of these lost varieties possess traits we urgently need: disease resistance, drought tolerance, nutritional properties. Seed banks sometimes contain samples that match the ancient DNA, varieties considered obsolete but potentially valuable in new contexts. The analysis reveals not just what was grown but networks of exchange, showing how crops spread across continents, adapted to new environments, diversified into regional varieties. Ground, penetrating radar and LiDAR transformed landscape archaeology. Flying over dense jungle, LiDAR sees through vegetation to reveal terrain below. In Central America, it revealed extensive Maya cities previously unknown. Sophisticated urban planning, agricultural terraces, water management systems, entire civilizations hidden under forest canopies. The technology shows that ancient landscape modification was far more extensive than visible remains suggested. Terraces, canals, roads, structures that would take decades to discover through traditional survey appear in LiDAR scans within days. Residue analysis on pottery reveals ancient diets and cooking methods. Lipids absorbed into ceramic surfaces survive millennia. Analysis identifies what was cooked in specific vessels: dairy products, meat, grains, fermented beverages. This recovers knowledge of food preparation that texts rarely describe in detail. We learn that ancient peoples processed foods in sophisticated ways, used specific vessels for specific purposes, created culinary traditions more complex than we recognized. Multispectral imaging reads text that is invisible to the naked eye. Manuscripts where text was erased and written over, where ink faded beyond legibility, where damage obscured words. Imaging at different wavelengths reveals what is hidden. Lost works emerge from palimpsests. Earlier versions of known texts appear, showing how they evolved. Each recovered text is knowledge returned from oblivion. The pattern is consistent. Almost every time we develop new analytical capabilities and apply them to ancient artifacts, we discover greater sophistication than we expected. Bronze Age swords show heat treatment techniques that indicate understanding of metallurgy more advanced than historians had assumed. Ancient dyes reveal chemistry that required precise control of oxidation and pH. Ancient peoples routinely worked with materials and methods we thought belonged to later periods. Our timeline of technological development keeps getting revised backward as science reveals what was already known millennia ago. Each new tool of analysis uncovers lost tools of creation, proving repeatedly that ancient peoples achieved more than we give them credit for. Deep underground in Malta, there is a chamber that does something peculiar to sound. The hypogeum of Thuviaal Saflieni was carved from limestone around 3000 BCE. A complex of rooms and passages used for burial and possibly ritual purposes. In one specific chamber, voices resonate at a frequency around 110 Hz with unusual intensity. Modern acoustical analysis confirms the effect. Speak or chant at certain pitches and the chamber amplifies the sound dramatically, creating resonance that seems to vibrate through bone and tissue. The architecture appears deliberately designed to create this effect. The shape of the space, the dimensions, the ceiling curvature, all contribute to focusing acoustic energy at this specific frequency. But we can only speculate about why. Some researchers suggest ceremonial purposes, that ancient priests understood how resonance at these frequencies affects human consciousness, creates altered states conducive to ritual experience. Modern analysis can measure the acoustics precisely, can confirm the sophistication of the design. What it cannot do is definitively explain the intention or how ancient builders achieved such precise acoustic engineering without computer simulations or acoustic modeling tools. At Puma Punku in Bolivia, modern laser scanning reveals precision that defies comfortable explanation. Stone blocks weighing multiple tons show surfaces flat to within fractions of millimeters, right angles accurate to tolerances that approach modern machining standards. The stones are diorite and andesite, among the hardest rocks on Earth. Experimental archaeology has attempted to demonstrate how such precision could be achieved with copper tools and stone abrasives, the implements ancient peoples supposedly possessed. The experiments achieve partial success with smaller stones and softer materials. They have not convincingly demonstrated the ability to create the precision found at Puma Punku in blocks of this size and hardness. No tools adequate to the task have been found at the site. We left measuring achievements we cannot fully explain, precision we cannot convincingly demonstrate how to replicate using proposed ancient methods. The Baghdad batteries present a different kind of mystery. These clay jars, dating from around 200 BCE to 200 CE, contain iron rods suspended inside copper cylinders. Fill them with acidic liquid, vinegar, wine, citrus juice, and they produce electrical current, about a volt or so. Modern replicas work perfectly well as primitive batteries, but we have no clear evidence of what they were actually used for. No ancient texts describe them. No surrounding artifacts suggest electrical applications. Some archaeologists argue they were used for electroplating gold onto silver, though evidence for this remains circumstantial. Others suggest they weren't intended as batteries at all, that the electrical properties are coincidental to some other purpose we don't understand. The objects exist. They function as batteries when used that way. Whether anyone in ancient Baghdad actually used them for electrical purposes remains uncertain. Polynesian navigation represents knowledge we're struggling to recover, despite its relatively recent practice. Navigators settled the vast Pacific, finding tiny islands across thousands of miles of open ocean, using techniques that integrated reading wave patterns, star positions, bird flight patterns, cloud formations, and subtle environmental cues into a comprehensive wayfinding system. Some of this knowledge survived into the modern era. Efforts to preserve and revive traditional navigation have achieved impressive successes. Reconstructed voyaging canoes crossing ocean distances using traditional techniques, but practitioners acknowledge they recovering fragments. The full sophistication of the original navigation systems, the depth of environmental knowledge encoded in traditional teaching methods, the integrated understanding that allowed voyagers to confidently set out across empty ocean, knowing they would find their destination. Much of this is lost. We can see that it worked. We can partially reconstruct how it worked. We cannot fully recover the complete knowledge system. Ancient astronomical observatories track celestial events with precision that seems unnecessary for practical purposes like agricultural calendars. Sites around the world align with solstices, equinoxes, lunar cycles, even more subtle celestial patterns. The precision suggests deliberate, sophisticated astronomical knowledge, but the purposes sometimes remain unclear. Was this purely ceremonial, embedding cosmic significance in religious architecture? Was it practical observation for purposes we don't recognize? Did ancient astronomers understand things about celestial mechanics that we assume they could have known? What unites these mysteries is evidence of capability without complete explanation. Modern analysis confirms the sophistication. We can measure the acoustic resonance, the stone-cutting precision, the electrical output, the astronomical alignments. What we often cannot do is fully explain how these were achieved or why. The knowledge was never adequately documented. The practitioners are centuries or millennia dead. The cultural context that made these capabilities meaningful is lost. We're left with artifacts and achievements that resist complete understanding, despite our best analytical tools. Reminders that some lost knowledge may remain permanently beyond our grasp. We tell ourselves a comfortable story about human history. It goes like this: humanity started primitive and has steadily progressed toward increasing sophistication. We began in caves with stone tools and gradually developed better technologies, more advanced knowledge, superior understanding. The timeline points in one direction, upward, forward, always improving. By this narrative, we stand at the pinnacle, looking back at ancestors who knew less, could do less, understood less than we do. It is a reassuring story. It is also wrong. The evidence we've examined tells a different story, one of rises and catastrophic falls, of knowledge gained and lost, and sometimes gained again. Roman concrete outperforms modern formulations in specific applications. Ancient astronomers tracked celestial mechanics with precision that took European science centuries to rediscover after the knowledge was lost. Surgical techniques practiced routinely in ancient India disappeared from European medicine for over 1,000 years. These aren't anomalies. They're patterns that challenge the linear narrative we've constructed about human progress. The idea of inevitable linear progress emerged largely from Enlightenment thinking, a philosophical framework that saw history as humanity's steady climb from darkness toward light. This perspective served useful purposes, motivating scientific inquiry and social reform. But it also created blind spots. making it difficult to acknowledge that ancient peoples might have possessed capabilities we lack. When we find evidence of sophisticated ancient technology, our first instinct is often disbelief, followed by tortured attempts to explain how primitive peoples could have achieved results that seem to require advanced knowledge. The simpler explanation, that they weren't primitive, that they possessed genuine expertise in domains we've neglected or forgotten, conflicts with our assumptions about progress. Archaeological discoveries keep pushing back our timelines. Complex structures appear earlier than we thought possible. Sophisticated tools emerge in contexts where they supposedly shouldn't exist. Evidence of abstract thinking, artistic expression, technological capability appears among peoples we assumed were too ancient to possess such sophistication. Each discovery forces revision, yet the fundamental narrative of linear progress persists, endlessly accommodating exceptions rather than questioning whether the model itself is flawed. Alternative models fit the evidence better. Perhaps human development is cyclical, civilizations rising to great heights, then collapsing, losing accumulated knowledge, forcing later generations to rediscover what was lost. Perhaps it is punctuated, rapid advances during certain periods followed by long plateaus or even regressions when circumstances change. Perhaps it is parallel, different civilizations independently developing similar solutions, suggesting that human ingenuity tends to rediscover certain fundamental principles even when knowledge has been lost elsewhere. Any of these models accommodates the evidence better than simple linearity. What the pattern of technological loss reveals is uncomfortable. Knowledge is fragile. It doesn't preserve itself automatically. It requires continuous transmission, economic support, cultural valuing, institutional maintenance. Break any of these links and sophisticated knowledge can vanish within a generation. What seems obvious to people who practice a technology daily becomes mysterious once the practice stops. The wheel was apparently invented multiple times in human history, forgotten in some places, preserved in others. If something as fundamental as the wheel can be lost, anything can. This challenges our technological triumphalism. Yes, we have smartphones and space stations, but we've also lost the ability to build concrete that self-heals over centuries. We've lost understanding of sustainable agricultural systems that maintained productivity for thousands of years. We've lost knowledge of materials, techniques, and practices that our ancestors considered routine. Progress isn't a simple accumulation of capabilities. It is often an exchange, gaining new abilities while losing old ones, sometimes without realizing what we've traded away until we need it and discover it is gone. The implications for our own era are sobering. What are we losing right now? Traditional craft knowledge disappears as elder practitioners die without successors. Indigenous languages vanish at unprecedented rates, taking with them ecological knowledge refined over millennia. Local agricultural varieties are displaced by industrial monoculture. Repair skills evaporate as we shift toward disposable consumption. Each loss seems small in isolation, economically rational, inevitable given changing circumstances. But collectively, we're experiencing knowledge loss on a scale that future generations might look back on the way we look back at the burning of Alexandria, wondering how people could have been so careless with irreplaceable knowledge. Recognizing that progress isn't linear isn't pessimistic, it is realistic. It means we can learn from the past rather than dismissing it as primitive. It means we can seek to recover valuable, lost knowledge rather than assuming everything old is inferior to everything new. It means we can preserve current knowledge more deliberately rather than assuming that valuable capabilities will automatically persist into the future. The story of human knowledge isn't a straight line pointing upward. It is a complex pattern of gains and losses, wisdom preserved and wisdom forgotten, capabilities achieved and capabilities abandoned. Understanding this pattern is the first step toward breaking it. Modern knowledge is both more abundant and more vulnerable than anything in human history. We possess more information, more technical capability, more accumulated understanding than all previous civilizations combined. Yet in crucial ways, we're more fragile than societies that carved knowledge into stone or passed it down through generations of direct teaching. The difference lies in how knowledge is distributed and what sustains it. No single person understands how to create a computer chip from raw materials. The knowledge exists, scattered across hundreds of specialists in geology, chemistry, materials science, electrical engineering, manufacturing, each expert in a narrow domain. The same applies to almost everything in modern life. Build a car from scratch. You'd need expertise in metallurgy, petroleum refining, rubber production, glass manufacturing, electronics, dozens of specialized domains. Produce antibiotics. You need microbiology, organic chemistry, pharmaceutical manufacturing, quality control systems. Modern knowledge is hyper-specialized and interdependent. This creates extraordinary efficiency. It also creates fragility. Break the chain at any point, lose the specialists in one crucial domain, disrupt the supply network, damage the infrastructure that connects everything, and capability vanishes despite the knowledge technically existing somewhere in the system. Much of what we know lives in digital form, utterly dependent on functioning technology. Files stored on servers require electrical grids, cooling systems, replacement hardware, technical expertise to maintain. A major solar storm, an electromagnetic pulse, a cascading failure in power systems could make vast amounts of digitally stored information inaccessible, not destroyed necessarily, but unreachable without the infrastructure required to access it. We're already experiencing this on smaller scales. Files from the early digital era sit on degraded floppy disks, stored in formats modern systems don't read, created by software that no longer exists. The data might technically still exist, but it is effectively lost because we can't access it. Corporate knowledge presents another vulnerability. Enormous amounts of technical knowledge exist only in proprietary databases protected by intellectual property law, never widely shared. Companies guard manufacturing processes, chemical formulas, engineering techniques as competitive advantages. If the company fails, if the servers are wiped, if the specialists disperse, that knowledge can simply disappear. It won't be in public libraries or academic journals. It will vanish as completely as the formula for Greek fire, leaving behind only products we can analyze but processes we cannot replicate. Previous generations possessed more individual resilience. A farmer knew how to grow food, preserve harvests, build shelter, repair tools. These weren't specialized skills requiring years of formal education. They were common knowledge maintained through practice and passed parent to child. Modern specialization means we're collectively capable of extraordinary things, but individually vulnerable. Most people in developed nations cannot produce their own food, build their own shelter, create their own tools, or generate their own energy. We depend entirely on functioning systems we don't personally understand. This works beautifully when systems function. It becomes catastrophic when they don't. The paradox is sharp. Humanity knows more than ever before, but a disruption that didn't kill people but did break technological infrastructure might cause knowledge loss exceeding anything in history. Not because the knowledge would be destroyed, but because it would become inaccessible. Locked in devices we can't power, formats we can't read, depending on expertise scattered across broken networks. There are positive developments. Distributed storage systems, open-source knowledge repositories, Wikipedia, and similar projects attempting to preserve information accessibly, the Internet Archive systematically capturing digital content, seed vaults protecting agricultural genetic diversity. These efforts matter, but they have limitations. Digital preservation requires ongoing energy, maintenance, and functioning technology. It is not passive preservation like carving into stone. It is active preservation that stops working the moment the supporting systems fail. Perhaps the most resilient knowledge is what we're losing fastest: practical skills, techniques that can be performed with local materials and knowledge, systems that don't depend on global supply chains or specialized infrastructure. Traditional agriculture using saved seeds and local resources, building techniques using local materials, repair skills that extend the life of existing tools. These represent appropriate technology, solutions scaled to local capability, maintainable without complex infrastructure. They're less efficient than modern alternatives. They're also more resilient against systemic disruption. As we lose this knowledge in favor of efficient but fragile systems, we're trading resilience for productivity, perhaps without fully recognizing what we're risking. Knowledge preservation isn't automatic, even in an information age. It requires deliberate effort, redundancy, and uncomfortable awareness that everything we know is more fragile than we'd like to believe. We inherit knowledge we didn't create. Everything we know, every capability we possess that extends beyond personal discovery, came from someone else. Ancestors who observed carefully, experimented patiently, solved problems creatively, and then chose to share what they learned rather than let it die with them. This inheritance carries obligation. We're not just beneficiaries, we're temporary custodians of accumulated human understanding, responsible for passing it forward intact, ideally expanded, but at minimum not diminished by our carelessness or neglect. The loss of knowledge impoverishes everyone who comes after. When a language dies, future linguists lose insights into human cognition and communication. When traditional ecological knowledge disappears, future generations lose understanding of sustainable relationships with specific environments. When ancient technologies are forgotten, future innovators lose potential solutions to problems we haven't yet encountered. We can't know what future circumstances will make valuable. Preserving diversity of knowledge, of techniques, of approaches maintains options for descendants facing challenges we cannot predict. What does this responsibility mean practically? It means supporting efforts to document endangered languages before the last speakers die. It means preserving genetic diversity in crops and livestock, rather than allowing industrial agriculture to erase millennia of selective breeding. It means maintaining traditional crafts and skills, even when they're economically uncompetitive with modern alternatives, recognizing that the knowledge itself has value beyond immediate profit. It means creating redundant repositories for crucial knowledge, not depending on single institutions or technologies that could fail. It means teaching practical skills, not just abstract information, ensuring people know how to create and repair, not just consume. Successful models exist. The Svalbard Global Seed Vault in Norway stores seeds from crop varieties worldwide, preserving genetic diversity against catastrophe. Oral history projects document elder knowledge before it is lost, creating archives that preserve not just facts but voices, perspectives, lived experience. Open source movements make knowledge freely available, ensuring that crucial information doesn't depend on corporate survival or institutional continuity. Community workshops maintain traditional crafts, passing skills directly from practitioner to apprentice, keeping knowledge alive through practice rather than just documentation. But challenges are substantial. Knowledge preservation competes with immediate concerns for limited resources and attention. Traditional knowledge holders are often marginalized, economically disadvantaged, their expertise undervalued by societies focused on formal credentials and modern techniques. Market forces push relentlessly towards standardization and efficiency, making diverse approaches economically unviable, even when they're culturally valuable or technically superior in specific contexts. Individual responsibility matters. You don't need institutional authority to participate in knowledge preservation. Learn practical skills, cooking from scratch, basic repair, gardening, traditional crafts, keeping knowledge alive through personal practice. Support craftspeople and traditional practitioners economically, creating markets that make their knowledge viable. Document family and community knowledge before elders die, recording not just what they know but how they learned it, why it matters. Question technological dependencies, understanding what you actually know versus what you depend on systems to provide. Teach the next generation not just to consume but to create, to repair, to understand rather than just use. Is all knowledge worth preserving? Some argue we should let obsolete technologies fade, that attempting to maintain everything dilutes effort better spent on the future. The counter-argument is humility about prediction. Roman concrete seemed obsolete when modern formulations were developed. Now we recognize its superior durability and sustainability for specific applications. Traditional crop varieties seemed inferior to modern hybrids bred for yield. Climate change makes their diverse resilience increasingly valuable. We cannot reliably predict what future circumstances will make useful. Preserving diverse knowledge maintains options for contexts we haven't imagined. This isn't nostalgia or rejection of progress. It is recognition that knowledge has value beyond immediate utility, that diversity provides resilience, that current optimal solutions might not be optimal under different conditions. It is understanding that we stand in a long chain of transmission, inheritors from the past and ancestors to the future, with responsibility to both. Throughout history, humanity has lost extraordinary knowledge through catastrophe, disruption, and neglect. The Library of Alexandria burned. Languages died taking irreplaceable knowledge with them. Economic changes made traditional crafts obsolete and their expertise vanished. Each loss diminished our collective capability. We have tools our ancestors lacked: digital storage, global communication, institutional resources dedicated to preservation. We also have unique vulnerabilities and unprecedented rates of change. Whether we preserve knowledge better than previous generations or lose it faster remains an open question, answered by choices we're making now. Every skill you learn, every traditional practice you support, every piece of knowledge you document and pass forward is an answer to that question, a small act of resistance against forgetting. Modern architects studying termite mounds in Africa discovered something remarkable. The insects maintain stable internal temperatures in their colonies, despite external temperatures that swing dramatically between scorching days and cool nights. They do this without mechanical systems, using only the architecture itself, carefully designed tunnels and chambers that create airflow through natural convection, warm air rising, and pulling cooler air from lower chambers in a continuous circulation. This biological engineering inspired the design of the Eastgate Center in Zimbabwe, a large office complex that maintains comfortable temperatures using 90% less energy than comparable buildings with conventional air conditioning. The principle wasn't new. Ancient peoples in hot climates had observed these same patterns and built structures using similar principles. We're rediscovering through scientific analysis what they understood through careful observation. Traditional architecture across the Middle East, North Africa, and parts of Asia incorporated wind towers, thick walls with high thermal mass, strategic window placement, and underground chambers that used Earth's stable temperature for cooling. These weren't primitive solutions. They were sophisticated applications of thermodynamics, achieved without equations or computer models, through observation of how air moves, how materials store and release heat, how building orientation affects temperature. Modern sustainable architecture is increasingly incorporating these ancient principles, recognizing that passive systems often outperform energy-intensive mechanical solutions in appropriate contexts. Water harvesting in arid regions demonstrates similar sophistication. Ancient peoples in areas with minimal rainfall developed techniques for capturing and storing every available drop. Systems in India, the Middle East, and the Americas used landscape contours to channel seasonal runoff into storage tanks, employed surface treatments that increased water collection, created underground cisterns that minimized evaporation. They understood watershed dynamics through observation, knew which soils filtered water naturally, recognized which plants indicated water sources. Modern climate-resilient water management is reviving these techniques, finding that ancient systems often outperform modern infrastructure in capturing and conserving water in challenging environments. Indigenous fire management challenges our entire approach to forestry. For generations, Western forestry policy suppressed all fires, viewing them as purely destructive. Indigenous peoples in Australia, North America, and elsewhere used controlled burns systematically, creating landscape mosaics of different vegetation ages that prevented catastrophic wildfires, maintained habitat diversity, and promoted the growth of useful plants. Modern fire ecology is recognizing what was dismissed as primitive practice was actually sophisticated land management based on deep understanding of ecosystem dynamics. Areas managed with traditional burning practices experience less severe wildfires and support greater biodiversity than areas managed with fire suppression. Traditional food preservation techniques are being recognized not just as historical curiosities but as health-promoting technologies. Fermentation, practiced across cultures for millennia, preserves food while creating beneficial bacteria that modern research shows support gut health and immune function. Drying, salting, smoking, techniques developed long before refrigeration, maintain nutrition while creating products with flavors and properties industrial processing cannot match. These aren't inferior alternatives to modern preservation. They're different approaches with different benefits, increasingly valued as we recognize that industrial food processing often sacrifices nutrition and health for convenience and shelf life. Traditional agriculture's emphasis on diversity over monoculture, on soil building rather than chemical inputs, on closed-loop systems where waste from one process feeds another, addresses challenges modern industrial agriculture faces. soil depletion, chemical dependency, vulnerability to pests and diseases. These problems emerge from approaches optimized for short-term yield rather than long-term sustainability. Traditional agricultural systems maintained productivity for centuries or millennia by working with ecological processes rather than against them. Modern sustainable agriculture is rediscovering principles that traditional farmers never forgot in cultures that maintained those practices. The pattern is consistent. Ancient peoples solved problems we're currently struggling with, often using less energy and fewer resources than modern approaches. They achieved sustainability not through advanced technology, but through deep observation of natural systems and patient refinement of techniques over generations. The distinction between primitive and advanced is misleading. Ancient solutions were sophisticated, optimized for different values than modern technology, sustainability over efficiency, resilience over yield, working with natural systems rather than attempting to dominate them. As we face resource constraints and environmental challenges, these ancient approaches become increasingly relevant, not as historical artifacts, but as practical solutions. The future might require combining ancient wisdom about working with natural systems with modern capabilities for analysis and implementation, creating solutions neither ancient nor modern, but integrated, drawing from the full breadth of human knowledge across time. Laboratories at MIT and other research institutions are developing concrete formulations inspired by a recipe 2,000 years old. They're not just recreating Roman concrete for historical interest. They're trying to solve a modern crisis. Contemporary concrete infrastructure degrades, requiring constant maintenance and eventual replacement at enormous cost and environmental impact. The concrete industry accounts for roughly 8% of global carbon emissions. If we could create concrete that strengthened over time instead of crumbling, that lasted centuries instead of decades, the implications would be transformative. Roman concrete demonstrates this is possible. Modern research is attempting to understand the chemistry well enough to replicate and improve upon it, creating self-healing materials that could revolutionize construction. The work goes beyond simple recreation. Researchers analyze why the Roman formulation works, the volcanic ash chemistry, the reaction with seawater, the formation of strengthening minerals over time, and then apply modern materials science to optimize the process. They're developing concrete that incorporates the self-healing principles Romans discovered empirically while adding modern understanding of chemistry and engineering. The result isn't ancient or modern, it is integrated knowledge drawing from both eras. Ancient silk production informs modern biomaterial research. For millennia, various cultures processed silk from different sources, creating textiles with remarkable properties, strength exceeding steel by weight, flexibility, biocompatibility. Modern materials scientists studying these traditional techniques are developing synthetic biomaterials for medical applications, protective fabrics, and structural components. Understanding how ancient peoples processed silk proteins, controlled fiber formation, and created specific material properties guides contemporary research into protein-based materials that could replace petroleum-derived synthetics. Research into ancient adhesives reveals formulations that modern chemistry hasn't improved upon for specific applications. Egyptian boat builders created waterproof adhesives from natural resins that have kept wooden vessels together for thousands of years. Native Americans developed tree resins into adhesives for attaching stone points to wooden shafts, bonds that remain intact in artifacts centuries old. These natural formulations often outperform modern synthetic adhesives in durability, while being completely biodegradable. As environmental concerns push research towards sustainable materials, ancient adhesive technologies are being studied seriously. Their chemical compositions analyzed, their properties tested, with an eye toward developing modern biodegradable adhesives that could replace petroleum-based products. Damascus steel's accidental nanoengineering has influenced modern metallurgy. When researchers discovered that ancient smiths were creating carbon nanotube structures through empirical process refinement, it opened new approaches to materials design. If ancient techniques could produce nanostructures without understanding what they were creating, modern engineers with full theoretical knowledge and advanced tools should be able to deliberately design materials at the nanoscale with even better properties. The discovery inspired research into how traditional metalworking processes affect material structure at microscopic scales, informing development of modern alloys and composites. Ancient pigments are being investigated for cutting-edge applications. Egyptian blue's property of fluorescing in infrared, unknown to its creators, has potential uses in medical imaging where infrared fluorescence could improve diagnostic capabilities, and in telecommunications where materials with specific optical properties are valuable. Maya blue's extraordinary chemical stability, resistant to acids, bases, heat, and biodegradation, is inspiring research into protective coatings for art conservation, industrial applications, and even spacecraft components that need to withstand harsh conditions without degrading. Traditional ceramic techniques inform modern advanced ceramics used in electronics, aerospace, and medical devices. Ancient potters achieved sophisticated control over glaze chemistry, firing atmospheres, and temperature profiles, creating specific colors, textures, and material properties. Modern ceramics engineers study these traditional techniques, finding that ancient approaches sometimes suggest solutions to contemporary challenges in creating materials with precise properties. The broader pattern challenges assumptions about progress. Ancient materials weren't inferior simply because they were developed empirically. They represent centuries of systematic experimentation, vast numbers of trials refined into reliable techniques. Modern science adds analytical capability, allowing us to understand why ancient formulations worked and potentially improve them. But the foundation, the experimental data, the proven techniques, the materials that demonstrably achieved remarkable properties comes from ancient knowledge. This isn't nostalgia. It is practical innovation, recognizing that ancient peoples conducted millennia of materials research, accumulated experimental data across countless applications and environments, and achieved results worth studying seriously. Mining this knowledge for insights, combining ancient discoveries with modern analytical capabilities, produces materials science that draws from the full depth of human experience with materials across all of history. The future of materials might be found by looking backward, understanding what worked before, and building upon foundations laid by people who couldn't see nanotubes but somehow learned to create them anyway. A Chinese herbalist in the 1960s named Tuesday Yuyo was searching ancient medical texts for treatments that might help with malaria, a disease killing millions. She found references to Qinghao, sweet wormwood, used for fevers for over 1,000 years. Following traditional preparation methods with some modifications, she isolated artemisinin, a compound that has since saved millions of lives and earned her a Nobel Prize. This wasn't a lucky accident. It was ancient knowledge validated by modern science, traditional observation confirmed through contemporary research. The pattern repeats across pharmaceutical history. Aspirin derives from willow bark, used for pain and fever across cultures for millennia before anyone understood salicylic acid. Digitalis from foxglove treated heart conditions in traditional European medicine long before modern pharmacology, explained how cardiac glycosides work. These aren't anomalies. They re-examples of a broader reality. Traditional medicine identified genuinely effective compounds through systematic observation over centuries. Modern science adds understanding of mechanism, ability to isolate and synthesize active ingredients, capacity for quality control, and dosing precision. But the foundation, knowing which plants treat which conditions, came from traditional knowledge. Pharmaceutical companies now engage in systematic bioprospecting, screening plants used in traditional medicine for bioactive compounds. The success rate is striking. Plants used traditionally for specific conditions often contain compounds that modern analysis confirms are relevant to those applications. Traditional anti-inflammatory herbs contain compounds with measurable anti-inflammatory effects. Traditional antimicrobials contain substances that laboratory testing shows inhibit bacterial growth. This validates what traditional healers maintained through generations. They weren't guessing. They were observing what worked and refining their understanding through accumulated experience. The validation raises ethical complexities. When pharmaceutical companies develop profitable drugs from traditional knowledge, who benefits? The indigenous peoples who maintained that knowledge often see no compensation. The plants they identified as valuable are patented by corporations that profit enormously, while the original knowledge holders remain economically marginalized. Efforts to address this through benefit sharing agreements face challenges of implementation and enforcement. Modern medicine is gradually incorporating traditional practices once dismissed as unscientific. Acupuncture for pain management now appears in mainstream medical settings, supported by research showing measurable effects on pain perception and inflammation. Herbal medicines are used alongside pharmaceuticals, with growing research into how traditional formulations work and potential interactions with modern drugs. Mindfulness practices derived from ancient meditation traditions are prescribed for anxiety, depression, and chronic pain, validated through neuroscience research, showing measurable changes in brain activity and stress responses. Traditional surgical techniques are being reconsidered. Ancient Indian rhinoplasty methods, preserved in texts and practice, inspired modern plastic surgery. Traditional bone setting techniques in various cultures achieve good outcomes without the metal implants modern orthopedics routinely uses, suggesting alternative approaches worth studying. Indigenous wound care using plants with antimicrobial properties is being investigated as antibiotic resistance makes alternative treatments increasingly urgent. The pharmacological knowledge at risk is staggering. As traditional healers die without successors, as languages disappear, as species go extinct, we lose potential treatments before identifying them. Traditional antimicrobial compounds might offer alternatives as antibiotic resistance renders current drugs ineffective. Ancient mental health practices might address aspects of psychological well-being that modern psychiatry overlooks. Traditional dietary wisdom might prevent chronic diseases that modern medicine struggles to treat. The challenge lies in integration. Modern medicine values controlled trials, isolated compounds, measurable outcomes. Traditional medicine often uses complex formulations, holistic approaches, treatments individualized to specific patients. Both systems have value, both have limitations. The question is how to bridge them. Studying traditional remedies with scientific rigor while respecting their context and complexity, learning from traditional diagnostic approaches while applying modern analytical tools. This isn't about replacing modern medicine. It is about enriching it, recognizing that traditional medical systems represent millennia of human experimentation with what helps and what harms. Ancient healers conducted countless trials, observed what worked, refined their approaches across generations. They created knowledge systems that, while lacking modern theoretical frameworks, possessed practical effectiveness validated by centuries of use. As traditional medical knowledge disappears at accelerating rates, we're losing a library we haven't finished reading, treatments we might desperately need as current approaches fail and new challenges emerge. We've traveled through millennia of forgotten knowledge, touching the edges of civilizations that rose and fell, carrying with them secrets we're still trying to rediscover. And if there is one truth that echoes through every story we've uncovered, it is this: progress has never been what we thought it was. We're told that history moves in one direction, forward, upward. That each generation stands on the shoulders of the last, building something taller, something better. But the catacombs beneath Rome, the unfinished obelisks of Egypt, the lost recipe for Greek fire, they tell a different story. They whisper that knowledge is fragile, that entire civilizations can forget how to do things their ancestors did effortlessly. That being advanced doesn't mean you're immune to losing what matters most. So what is progress really? If it is not this clean, unbroken line marching towards some technological singularity, then what should it be? Perhaps genuine progress isn't just about gaining new capabilities. It is about preserving the ones we already have. It is not just efficiency, it is resilience, not just growth, but sustainability. Not just the rush to innovate, but the wisdom to know when innovation serves us and when maintenance, when preservation, is what we actually need. There is a concept that doesn't get enough attention: appropriate technology. It is the idea that the best solution isn't always the most technically sophisticated one. It is the solution optimized for context, for the people who'll use it, for the environment that sustains it, for the future that depends on it. Sometimes, more often than we'd like to admit, ancient technologies fit these criteria better than anything we've designed in the last century. Roman concrete that heals its own cracks, Incan agricultural terraces that prevent erosion while maximizing yield, Persian wind catchers that cool buildings without electricity. These weren't primitive attempts at solutions we've now perfected. They were, in many cases, better answers to fundamental problems than what we're using today. This should change how we think about knowledge itself. Diversity isn't just nice to have, it is survival insurance. When we preserve different approaches, different techniques, different ways of understanding the world, we're building resilience against challenges we can't yet imagine. Local knowledge, traditional practices, indigenous wisdom, these aren't charming relics. They're repositories of solutions tested across centuries, refined through countless iterations, proven in ways that laboratory research, for all its value, simply cannot match. And there is another layer. Some knowledge can't be written down. It lives in hands that have practiced a craft for decades. It exists in the intuitive understanding that comes only from direct, prolonged experience. When we lose the practitioners, we lose something books cannot preserve, something videos cannot capture. We lose the tacit, embodied knowledge that made ancient achievements possible. What would education look like if we understood this? Would we still organize learning around the assumption that theoretical, academic knowledge is inherently superior to practical hands on mastery? Would we teach only STEM subjects, or would we value traditional crafts, practical skills, diverse knowledge systems as equally essential to a functioning society? The economics matter too. If we genuinely value knowledge preservation, we need systems that support traditional practitioners, master craftspeople, knowledge holders, even when their work doesn't scale efficiently, even when it is not maximally profitable. Because the real cost of losing their expertise only becomes clear after they're gone. And what about innovation itself? What if technology companies, before assuming high-tech solutions are superior, actually studied traditional approaches? What if researchers consulted indigenous knowledge holders as experts rather than dismissing their insights as merely anecdotal? What if institutions open-sourced their discoveries instead of hoarding proprietary knowledge that vanishes when companies fail or priorities shift? There is a phrase for what this could become: innovation with memory, new developments that incorporate rather than erase what came before. Advances that build upon accumulated wisdom instead of arrogantly assuming everything old is obsolete. We see glimpses already: modern water systems integrating ancient rainwater harvesting, sustainable architecture combining passive design principles with contemporary materials, agricultural methods blending traditional polyculture with modern soil science. Real progress isn't leaving the past behind. It is carrying forward everything valuable we've learned while building something new. The question was never whether to look backward or forward. It is how we learn to do both simultaneously, how we expand our toolkit instead of just replacing tools we don't fully understand. We don't have all the answers. Ancient peoples solved real problems often more effectively than we do. And recognizing that doesn't make us less advanced. It makes us mature enough to learn. Knowing what we've lost is only half the equation. The other half is deciding what we're going to do about it. And the truth is, preservation isn't something that happens in government offices or university archives. It starts smaller than that. It starts with you, in your kitchen, in your neighborhood, in the choices you make about what deserves your time and attention. Learn something with your hands. Cook a dish from scratch instead of opening a package. Fix something broken instead of throwing it away. Grow something, even if it is just herbs on a windowsill. These aren't quaint hobbies, they're acts of preservation. Every skill you practice is a thread connecting you to centuries of human knowledge, and every thread makes the larger fabric stronger. Talk to the people who still remember, your grandmother who gardens without looking at instructions, the neighbor who repairs furniture instead of buying new, the elder in your community who speaks a language fewer people know each year. Record their stories, write down their techniques, ask them to show you, not just tell you, because some knowledge only transfers through demonstration, through the feeling of doing it yourself under the guidance of someone who has done it 1,000 times. Support the people keeping traditions alive. When you buy from a craftsperson instead of a corporation, you're voting with your resources for a world where mastery still matters. When you attend cultural events, when you value quality over convenience, when you're willing to pay more for something made with knowledge that took years to acquire, you're creating economic conditions where preservation becomes possible. But individual action, essential as it is, isn't enough. Communities have power that individuals don't. A makerspace where people can learn forgotten skills. An oral history project capturing local knowledge before the people who hold it are gone. A seed library preserving agricultural varieties that corporations abandoned because they weren't profitable enough. A skill sharing network where the person who knows how to preserve food teaches the person who knows how to repair electronics, and both walk away with knowledge they didn't have before. These community structures create resilience. When knowledge lives in multiple people, in multiple places, it is harder to lose. When it is actively practiced, passed from person to person through living networks rather than stored passively in books or databases, it stays vital. It evolves. It adapts. It remains useful rather than becoming a museum exhibit. Larger systems matter too. Policy can fund the documentation of endangered knowledge before it vanishes. It can support indigenous land rights, recognizing that traditional resource management often outperforms modern alternatives. It can reform education to include practical skills alongside theoretical knowledge, to teach multiple ways of understanding the world instead of privileging only one. Economic incentives can support apprenticeships, grants for traditional practitioners, markets for sustainable products made using methods worth preserving. Technology has a role here, but it is complicated. Digital documentation can capture practices that would otherwise disappear. Online platforms can connect knowledge holders with people desperate to learn. Virtual reality might preserve spatial understanding in ways text and photos cannot. But technology is a tool for preservation, not preservation itself. A video of someone weaving doesn't preserve weaving. Teaching someone to weave preserves weaving. There are models that work. New Zealand integrating Morti traditional knowledge into environmental management. Italy's slow food movement keeping culinary traditions alive and economically viable. Japan designating master craftspeople as living national treasures, providing them resources to teach the next generation. Indigenous-led initiatives documenting traditional knowledge on their own terms, controlling how it is shared and who benefits. The challenges are real. Economic pressure makes traditional practices feel like luxuries people can't afford. Power imbalances marginalize the voices of those holding traditional knowledge. Generational divides create friction between valuing the old and embracing the new. But these aren't insurmountable. They're design problems. And humans are good at solving design problems when we decide something matters. Every skill you learn, every tradition you support, every elder you listen to is an act of resistance against forgetting. Preservation isn't about freezing knowledge in amber. It is about keeping knowledge alive, practiced, passed on, ready to inform solutions to problems we haven't encountered yet. The question isn't whether we can preserve what matters, it is whether we will. We began this journey standing before structures we couldn't fully explain, holding artifacts we couldn't completely replicate, ancient achievements that seemed impossible, that tempted us towards stories of lost civilizations far more advanced than ours, or visitors from distant stars who left their mark and vanished. But now, after traveling through centuries of forgotten knowledge, we see these mysteries differently. They're not evidence of magic or extraterrestrial intervention. They're testament to human ingenuity, to the extraordinary things ordinary people can accomplish when knowledge accumulates across generations, when communities devote themselves to mastery, when solutions are refined through countless iterations over spans of time we can barely imagine. This is what makes us human. We remember. We build upon what came before. We pass forward what we've learned so that our children don't have to start from nothing. No other species does this like we do. This transmission of culture, this accumulation of understanding that lets each generation stand on the shoulders of everyone who came before. But we also forget spectacularly, repeatedly. Entire libraries of knowledge vanish when teaching lineages break, when catastrophes strike, when economic pressures make traditional practices unviable. We are the species that remembers and the species that forgets, walking forward on the shoulders of giants, while stepping over the scattered pieces they dropped along the way. The ancient peoples we've encountered in this story deserve something from us. Not our condescension, not our assumption that they were primitive attempts at what we've now perfected. They deserve our respect. They solved real problems with remarkable sophistication. They understood things about materials, about structures, about working with their environment that we're still trying to relearn, and their achievements remind us of uncomfortable truths. Knowledge is more fragile than we imagine. What seems permanent, essential, impossible to lose can vanish within a generation. The recipe for Greek fire, the technique for forging Damascus steel, the method for creating Roman concrete that lasts millennia gone. Not because the knowledge was trivial, but because the chain of transmission broke. Every lost technology, every vanished language, every forgotten technique represents human lives. People who devoted themselves to mastering something, who created something remarkable, who tried to pass it forward but couldn't complete the transmission. Their work survives only in fragments, in mysteries that perplex us, in questions we're still trying to answer, and that should shape how we live now. Every choice we make about what to preserve, what to teach, what to value, it determines what knowledge survives into the future. We are all links in a chain stretching from ancestors we'll never know to descendants who'll inherit whatever we choose to pass forward. This isn't just about ancient techniques. It is about languages spoken by fewer people each year, traditional ecological knowledge that could help us adapt to climate change, practical skills that make people resilient and self-reliant, ways of thinking about problems that offer alternatives to approaches that aren't working. Every time one of these vanishes, we lose options, we lose diversity, we lose resilience against challenges we haven't encountered yet. But there is hope woven through this story too. Knowledge can be recovered, traditional practices can be revived, endangered languages can be preserved. It takes effort, resources, intention, but it is possible. Every successful revival, every skill relearned, every tradition maintained is a victory against forgetting. Lost technologies aren't evidence that we're inferior to our ancestors or that they were superior to us. They're evidence that knowledge is a collective human treasure, accumulated slowly, lost easily, and worth protecting with everything we have. We are temporary stewards of humanity's accumulated understanding. What we do with that responsibility, whether we preserve and expand and transmit, or whether we allow loss and fragmentation, will determine what inheritance we leave. The story of lost technologies isn't finished. We're living it right now. Future generations will look back at this moment and judge what we preserved and what we allowed to disappear. We're all standing in a vast library built across millennia, surrounded by knowledge inherited from countless generations. What will you preserve? What will you learn? What will you teach? The answer is being written right now in every choice you make.